All right.
We're back.
We're back.
Wow, that was quite the flurry of activity. For those of you out there who've been watching, you probably noticed that something went wrong. Our host platform had a pretty significant meltdown, and we needed to be moved over to a new kind of a redo in terms of the session. So
we have to clarify though that it is not the internet that was broken, so don't panic. Okay. It was in YouTube did not fail. So it was not the internet. So.
Nothing wrong with YouTube. So hopefully, fingers crossed, we'll have an uneventful rest of the session today. So with that out of the way.
Right. I mean, quick comment before you get started, Angelique, it's like, when something goes wrong, that this whole panic of, was it the internet? Was it my Wi-Fi? What happened? We all went through that right now. Again, hopefully we don't see that for the next 4 hours. But Angelique, I think maybe if you can go back a few slides and then, start from there, that might be beneficial for the audience.
Yeah, sounds good. So, and thanks, Archana, for taking over at some point. So, just kind of rewinding a little bit, going back to where we were, maybe about 15 minutes ago. So we covered the cloud providers and their stability, and we talked a little bit about they are very stable from both a performance and an availability standpoint, and how they simply have much fewer outages than ISP networks. Now, in looking at when these outages occur, it looks like they're primarily happening in maintenance windows. So let's take a look at the ISPs and see how they compare in terms of when these outages are occurring and where they're occurring. So next slide. So the number of outages does vary by region, but across the board, we did see changes in the numbers of disruptions, both in North America and Asia-Pac. When it came in the March period, we saw a really significant spike. Now, in both regions, the level of disruptions have slowly gone down to not quite normal, but pretty close to normal levels. Whereas in EMEA, we still see this smaller but increasing number of disruptions. It's not really clear what is causing that. Could be related to different changing traffic patterns across the different countries in relation to their shutdown and reopening activities. Next slide. Now, from the standpoint of performance, given that there was this increase in disruptions, was it perhaps due to network duress, maybe related to increasing network congestion? Now, in looking at the performance of the ISPs over this period, January through June, for both North America and Asia-Pac, next slide, we can see that there really are no significant differences. So there isn't a legend here, so just let me give you some orientation. The teal bars are indicating an increase, a percentage increase in latency, overall latency, and the red bar is packet loss. So in the March timeframe, we really didn't see any significant differences in terms of jitter, packet loss, or latency. Now, there was some increase in latency in April, and then again in May, and then in June, but that could also indicate that there are simply routes are being changed. From the standpoint of packet loss, really nothing of note until the June timeframe, and that was when outages were starting to come down already. So it doesn't seem like they're related to the number of disruptions that we're seeing. And that's the same in, for example, Asia-Pac as well. If you look at just performance there, Europe was very stable, and Asia-Pac, we really only saw some slight elevation in packet loss in the March timeframe. But other than that, performance was relatively consistent for the first half of 2020. Next slide. So given that performance did not seem to be impacted, there wasn't any significant evidence of, or really, any kind of evidence of network duress or congestion within networks on a systemic level, what was contributing to the rise in disruptions? if we look at how those disruptions impacted availability over the last several months, we can see that the increasing levels of unavailability from an infrastructure standpoint do correspond with some very significant shifts. So in the latter part of March, where we had in the United States, so we're just looking at North America now, we had shutdown orders in some of the largest states initially, California and New York, and then that was subsequently followed by others. Now, over the next couple of months, as reported by both ISPs as well as exchange providers and even CDN providers, there was still significant shift of traffic in terms of types of services that were being used. So for example, using more video conferencing, that was changing the amount of upstream, downstream bandwidth, for example, that was being consumed, as well as just in terms of the overall usage of the internet that was simply going up. So it may be that there were some adjustments being made by the network operators to accommodate these changes. Next slide. And staying on North America for a moment, we do see evidence of that in the nature of the outages themselves. So not only were there more outages, but the outages were much bigger, they were lasting longer, and they often were spread out over a wider geographic area. So they involved more cities. So we saw, for example, that in North America, the average number of interfaces involved in outages in, for example, February was around 7. And in March, that shot up to, on average, about 40 interfaces per outage. Now you can see here, this is an example of a transit provider that was having a really significant outage that involved hundreds of interfaces, and these outages were taking place for long periods of time, 30, 40, sometimes even longer than that. And oftentimes these would be periodic. So the breadth of these outages, their scope, are not indicative of congestion. They really point to something that's gone wrong in terms of the control plane. And so because of that, it's likely that it was something that was done by the network operator, either or to make a service change, and it either intentionally brought the network down or unintentionally. Next slide. But, what we saw with the cloud providers, it's not so much that there are more outages or that the outages are, for example, severe. They involve a lot of infrastructure. The more important piece to look at is, when are the outages occurring? Are they happening at a period of time where they would be very disruptive to businesses, or are they happening off hours, maybe during periods which are more indicative of maintenance? Next slide. So in looking region by region, we can see that, for example, North America, most of the disruptions, the pattern of disruption tends to weight towards off hours. So periods of time outside of business hours. Now in North America, we're looking at a window of time that's 9 to 5 Eastern time. But you can if you're on the West Coast, you can kind of mentally slide that over. But we can see that this pattern exists in January and February. The darker colors are business hours. And then as outages dramatically increase, and as the data set that we're looking at gets bigger, we can see this pattern is even more pronounced in March, for example, where most of the outages are taking place in those kind of latter hours of the day or in the early hours of the morning. So it seems like these are more intentional, just as we saw with cloud providers. Next slide. Now we see something very different in EMEA. Most of the outage peaks tend to take place in the late afternoon. Now, it may be that the network operators there have determined that that is based on their market and their customers, that is a time that's, not problematic in terms of outage events. That's not really clear, but what is clear is that they are taking place in kind of more of this later afternoon period of time, which may or may not, depending on their customers and their market, be disruptive from a user standpoint. Next slide. And then Asia Pac is a little bit less clear in terms of their preference. They tend to be more broadly distributed across various hours of the day. As outages increased in March, they did tend to increase more towards the early part of the morning hours, but they are still, fairly distributed overall, and that's something we still continue to see even today. Next slide. So that's just, what you can take away from that is that it's really important not only to understand the scope of a disruption, but also when it's occurring and even its duration, for example. So in looking at the number of outages that are happening during business hours, for example, in North America, it's quite a bit smaller percentage-wise than in other regions. So only about 25% are occurring during business hours, and many of them are very brief. So if we further reduce that and, kind of eliminate the ones that are, just a few minutes, it's actually quite a bit smaller than that. So even though there's been an elevation in the number of disruptions, they're not necessarily impactful from a business standpoint or from a user standpoint. Next slide. So we touched on some of the differences between cloud providers and internet service providers. Now, it's important to point out that cloud providers don't have some magic pixie dust. There are differences in internet service providers and the level of stability and performance that they offer. And some of this may have to do with factors related to some of the things we touched on, like technical debt and just the amount of legacy infrastructure that you're dealing with. So next slide. So in looking, for example, at both the US and South Korea. Now, these are very different markets. They have different policies and investments related to internet infrastructures and services. But just as a point of comparison, there are internet service providers that are very consistent and offer high level of performance. And, so it's not something that's necessarily uniform, and it's not necessarily something where cloud providers are always better than ISPs. It's really just that the operators themselves vary, and perhaps the less legacy or technical debt that you have as an operator that might contribute to your level of performance. Next slide. So what was interesting that we saw was that, we see that for many ISPs, in particular in North America, and for cloud providers, they tend to have these disruptions in off hours. So in looking at weekends, is it the case that there are more disruptions on weekends, given that there's less usage of the internet? Next slide. So in looking at ISPs, that doesn't seem to be the case. Across the board, across all regions, in particular in North America and EMEA, we can see that there are far fewer outages on weekends than there are on weekdays, even during business hours. So there doesn't seem to be a lot of activity taking place on weekends. And this is something that is even shared across cloud providers, and they seem to be very thoughtful about when these disruptions are taking place. Next slide. So you can see that there's hardly any outages that are taking place on weekends. It seems to be a pretty quiet period for both providers and both of these network operators. So that was just something interesting to see how they sort of shared that. Next slide. So to wrap up, we're running a little bit behind, so we're going to kind of power through this. Next slide. So overall, internet infrastructures have held up really well in terms of the disruptions we're seeing. There's no evidence that they were caused by any systemic degradation of performance or congestion or anything like that. They seem to be due to compensatory actions that the network operators have taken in order to accommodate changes in traffic, whether that be volume increases or patterns of usage. And so it may actually indicate that that's, a healthy response. And when there are changes to the network, it may be that there needs to be an adjustment period by the network operators. Next slide. So takeaways: cloud networks overall demonstrated greater stability. But not all outages impact users the same way. So even though there may be more disruptions within internet service providers, not all of them are disruptive to users, and stability and performance really does vary across region and across providers. So really need to understand how each of them work individually. It can vary pretty widely. Even within the US, we can see differences between different broadband providers. So with that, if you're interested in learning more, next slide, we're going to make this information and much more available, including some performance data related to CDN and DNS providers, and that's going to be released in a couple of weeks, so stay tuned. We're really excited to share that. So with that, Archana, I think we're ready for our panel.
I know, that's exciting. Angelique, thanks again. I know I've heard this data quite a bit from you, and we've been discussing this, but this was really great information. And again, guys, any questions in here, feel free to send this in and we'll get to it later. With that, I'm going to introduce our panelists for the next session, David Belson. David Belson is the Senior Director of Internet Research and Analysis at the Internet Society, and he is focused there on efforts around internet measurement, shutdowns, understanding market trends, and the impact of the growth of the internet across the globe. And before joining Internet Society, David had a very similar role with Oracle's Internet Intelligence team. And prior to that, he spent over 18 years in Akamai, and some of you are probably familiar with David's name from the State of the Internet report, which was Akamai's quarterly report series that he was kind of leading there. So with that, David, I'm going to pass it on to you.
Great, Archana. Thank you very much. And thank you, everybody, for joining us today. Next slide. There we go. Over the next half hour, I'm privileged to be leading a panel to talk about internet resiliency during COVID-19. It's a really interesting topic, and it's something that has really come to the forefront for so many of us over the last several months. Next slide. So in late February, early March, there was a lot of virtual ink spilled as everybody started to work from home and everybody was locked down around concerns that the internet might break. Was all of the increased traffic and the associated latency going to cause a lot of problems? Was it going to really slow things down? Was it really going to make it hard to watch Netflix videos or to do Zoom conferences or what have you? So a lot of articles out there. Here's a sample of a few of them. And in late February, I had published a blog post on the Internet Society blog called "Is the Internet Resilient Enough to Withstand Coronavirus?" Taking a look at some of the metrics that we needed to watch and see what happened. Next slide. So after a month or so, it became pretty clear that the internet was not going to break. It was able to withstand the strain. It was able to withstand the increased traffic. And I published a follow-up post that said, "Yep, the internet is resilient enough, but there is a catch." And that catch was more related to the digital divide, which is a topic for a separate webinar. But what we're really here today is to talk about how and why the internet was resilient and how it managed to stay up and largely problem free over the last several months. Next slide. So one key reason that the internet was so resilient or is so resilient is because it's a network of networks. There's no single monolithic internet to break. It's a combination of tens of thousands of different types of interconnected networks, mobile providers, last mile providers, backbone networks, academic networks, enterprise networks, internet exchange points, CDN providers, and so on. And to talk about that today, I've got three panelists representing an IXP, a content delivery network, and a last mile community network provider. So Jim Troutman, director at Nenix, Jaya Iyengar, distinguished engineer at Fastly, and Scott Rasmussen, a business development and strategic partnership representative from New York City Mesh. So Jim, you want to introduce yourself?
Yes. Hello and good day to all of you in whichever time zone you're attending from. My name is Jim Troutman. I'm a volunteer director and general purpose agitator for NENIX. We're a small not-for-profit internet exchange serving northern New England, which is Maine, New Hampshire, and Vermont, if you're not familiar. In our very rural region, NENIX tries to foster and promote increased internet resiliency and connectivity, higher broadband speeds at lower costs. In our region, it's still common for wholesale internet transit costs to exceed $5 per megabit per month, and there are still large areas where residential broadband is limited to low-speed DSL if it's available at all. My day job is an independent internet infrastructure consultant and IT architect, and I work with a variety of regional ISPs, telcos, and enterprises to help solve their problems.
Cool. Thank you, Jim. Johnny, you want to give a quick intro?
Sure. Thank you for bringing me in here, David. Well, my name is Jana Iyengar, and I am a distinguished engineer in the CTO's office at Fastly. Can you put the first slide up, please? Not that one. Anyways, I'll keep going while the slide comes up. So yeah, so I work on a number of things, but primarily on Quick, which we won't be talking about here. But Fastly, as a CDN company, it's basically what we call as an edge cloud platform, which basically means that we have a distributed system that's sitting, we have machines sitting all over the world, and we offer storage as well as compute from those machines. And so you do also perform the services of a traditional CDN. And the data that I'll be showing you today comes from a number of our customers that use the CDN there.
Thanks, Jenna. And those are the correct slides. You can hide those again. And finally, Scott, you want to give a quick intro to New York City Mesh?
Sure, absolutely. My name's Scott. I'm an organizer with NYC Mesh. As you mentioned, David, we're a community network based in New York. We connect about 500 buildings across the city. We're a nonprofit, and we believe that the internet is for everyone. So we have volunteers that build out our network. We're entirely run by volunteers and the people who own our network. And together we engage in popular education, network infrastructure building, and other sorts of activities needed to make sure that we can connect New Yorkers no matter what their home looks like or what they're able to afford.
Great, thank you, Scott. So today we want to look at resilience within the panel in three different areas. One is from a traffic perspective. One is from the challenges, so what challenges were faced, and then looking towards the future and looking at how we remain resilient. So the first question that I have for the panelists is what their traffic levels were like heading into the March lockdowns, and how they changed as a result of the lockdowns being implemented. So Jim, let's look at you first for NENIX and for the IXP community.
Yes. So NENIX, we saw quite a large traffic increase. We are small. We have a small number of peers, but we had approximately more than a 2x doubling of traffic. Around the world and in general for IXPs that I've talked with and monitored, everyone saw between 30 to 50% traffic increase during the lockdown. A lot of the IXs ended up deploying an entire year's worth of bandwidth upgrades and planned expansions in a matter of a month or two, just to be able to keep up with demand.
Great. And Jana, what about Fastly? What kind of traffic increases did Fastly see?
Yeah, so I have some data to show. If we can get the first Fastly, not the Fastly slide, but the data slide up. We definitely saw increases, and we actually published a blog post about this in, I can't remember, May it was. So you look up the Fastly blog page, you'll see that the slide before this. So I'll start with the, if you can.
Not that one. Go back to the New York, New Jersey slide.
That's fine. Yeah, I can pick it up from there. That's fine. So basically, one of the things that you see here is that so there's a lot going on this slide, and this is basically one of the deep dive slides. So I won't go into detail here. Just very broadly speaking, what we tried to do was we looked at internet traffic at our from our POPs. We looked at how traffic volume was increasing and how what we measured as download speed. We basically measured at our servers, we were measuring TCP delivery rate, and we measured that as a proxy for what download speed users were experiencing. And we looked at what happened to that when those connections were going to particular parts of the world. And so this one is looking at just New York and New Jersey. The red curve that you see there is basically the hockey stick. Unfortunate COVID cases increased that happened over time. The blue curve that you see rising up slowly is the traffic level increase that we saw in traffic going to New York and New Jersey, that region of the world. And the green curve down below that's decreasing, these are all percentage changes from just an arbitrary point. That shows download speed as we measured it. Now, you can see that traffic levels are definitely increasing. And as a result, we saw some of the download speed decrease, but it didn't completely go down. It went down at a much lower rate than the traffic increases. And we also see that it's sort of, towards the end, there's some recuperation, there's some improvement happening there on the download speed, despite the fact that traffic increases continued to happen through the end of March. Can you go to the next slide?
That was good to see then from the fact that the download speeds didn't drop significantly, I think certainly speaks to the resilience of the network infrastructure in that area.
Absolutely. And that's something that we saw repeatedly. So if you see the next slide, you'll see a similar trend again. This was in Italy. Again, you see a similar trend. I won't go into the details of various events there. The next slide shows you the UK. Can you go to the next slide, please? Yeah, so this shows the UK, and you see similar trends. A couple of things I'll note, because they're interesting, I think. One of the things is that we saw dramatic increases in traffic as school closures were announced, or kids went home, basically, because as children go home, parents go home, everybody goes home, and the traffic that we saw increased, and presumably this was mostly increase in residential areas. We didn't really dig into that much. But you also see these nice bumps in the UK. Those are weekend bumps, and those disappear. Yeah, those disappear completely. So
yeah, that was something I saw elsewhere as well. Comments from other network providers that the weekend shifts that you normally saw in their traffic went away. It's really interesting. So thank you. And so now that we're 3 or 4 months on from the lockdown orders and school is over, around here we're starting to talk about going back to school. Businesses are gradually starting to reopen. Some of the traffic graphs I've seen out there show that the peaks are kind of back around pre-lockdown levels. So where are your traffic levels at these days? And Jenna, I know you guys are a public company. Don't want to get you in trouble with anybody, so I'll give you a pass on this question. But Scott and Jim, if you can, say a few words on where your, the traffic levels that you're seeing now that things are, now that we're a quarter on.
Absolutely. Well, we're a wireless network for the most part. And prior to COVID, we were seeing generally when we do the back of the envelope math to figure out how much bandwidth we need in a particular area or backhaul, we generally average about 2 megabits per second per unit throughout the day. And that's kind of the average that we can operate with. That peaked at about 4.5 megabits per second per day. So we more than doubled kind of usage of our network on a daily basis. And then now it's settled back down to about 3 or so. So we really saw in the first week or two, an incredible peak of traffic, a lot of emergencies for us and our volunteers, but then things have actually gradually lowered as not only our network kind of optimized itself to be able to meet, increased demand, but also I think as things have changed, particularly probably school ending in New York City.
Can I get my slides with the statistics page? The green one. Most of the IXs have seen a little bit of a decrease in traffic. It's not back down to normal levels or levels pre-COVID, because just the growth of internet traffic is always happens.
Can we move ahead 2 slides? There we go. Thank you.
So you can see long-term trends at various IXs around the world. These graphs are from the start of the COVID period, but traffic levels have come down a bit as lockdowns are ending. On my non-IX work on the retail ISP side, definitely seeing that as well. And it's interesting, Scott, that what I see in our very rural area is more like 0.5 megabit to 1 megabit per user instead of 2 to 4. And that's simply because the access last mile isn't there, unfortunately.
Sounds like there's an opportunity for a main mesh up there, Scott.
Yeah, absolutely. So we're all in. We're ready.
Yes, we could talk.
Good area up there.
Could I have the next slide, please? And I just wanted to touch on the shape and the difference during COVID. That the bottom left there shows a typical period highlighted. And then during lockdown, the shape of traffic changed. It was basically kind of an all-day peak with a little bit of bumps. Another thing that was interesting, particularly in the IX world, is a lot of the large academic networks, like a lot of the K-12 and university networks, they were basically ghost towns during lockdown. However, they basically became content providers because a lot of people were accessing content and educational things that they provide. So it was an interesting role reversal, and that graph on the right side shows that.
Yeah, and interesting with respect to the K-12 networks, and I don't know if you have any visibility into this, but there were a lot of stories about in certain parts of the U.S. at least where students without network connectivity at home were basically sitting outside.
Absolutely. There was a whole network from car homework from car initiative in Maine. The Maine folks at Network Maine, they actually worked with a lot of the K-12 schools specifically to open up Wi-Fi hotspots and to get people to come in during the lockdown and like move access points close to a window, that sort of thing, just to get some sort of connectivity, because there's literally thousands and thousands of kids that were in lockdown that didn't have internet access at all. Yeah,
and that's where the resilience failed.
Absolutely.
But and which I think is actually a good segue to the challenges question. So were there specific challenges that your organization or infrastructure faced related to the COVID-driven increased usage? Jenna, as a CDN provider, I'm sure you guys are very used to sudden peaks in traffic, but can you speak to any of the challenges that Fastly saw?
Yeah, so this is basically what we do, right? I mean, it's our job to handle these things, and we were able to manage it. And as you saw in the graphs and in various graphs that we're seeing, basically, and as David, you said right at the beginning of this panel as well, it was another day, another sort of sustained peak that we saw for a while, and we were able to take it in our stride. This is, I want to say that this, yes, for Fastly, it definitely was something that we do, that's something that we're good at, and so we were able to do this. But at the same time, it also speaks to the value of a lot of innovation that's happened in the industry over the past 10, 15 years. I don't know if we could have really survived this, 20 years ago, 15 years ago. And one of my dear friends and colleagues, Patrick McManus, wrote a blog post about this, about basically the 4 key innovations that has allowed us to be resilient during this time. And I think it's important to recognize the value of all of these things. The standards and the specs of the internet are also designed for reliability, for elasticity, for resilience. And so we continue to build those standards, and they've been tested, and I think they've held up.
Yeah, absolutely. Cool. And Scott, can you speak to New York City Mesh?
Sure. I think our biggest challenges were twofold. One, centered on kind of human capacity. In New York, we were under a lockdown, so things like maintenance and the very basic types of things of getting across New York City, a city where most people don't own a car, and you're dependent on public transportation or anything else to schlep equipment across town.
And nobody was rushing to the New York City subways in the middle of COVID.
Exactly. And so we can talk a little bit more about that later, but the issue of kind of human capacity and what we were able to do was significantly limited and something that was trying for us. The other was spectrum. As I mentioned, we're a wireless network. New York is a very, very busy space in the radio frequency environment. Not only do we have 3 airports that we're operating around, but we have a lot of other users. And something that we found is that a lot more folks were jumping around channels trying to find, open opportunities or spaces that they could operate in to kind of increase bandwidth and meet those needs that we saw immediately after the lockdowns. And as that happens, obviously, then that starts a chain reaction of 10 other users of spectrum that are suddenly reshuffling around and moving around. So we had to be incredibly dynamic in our use. And interestingly, in many ways, it often got down to, again, a human question. We really had RF engineers watching and looking and actually manually selecting channels in which to operate in, because in many cases, things were moving, in some cases too quickly to be able to kind of leave it up to automatically kind of selecting channels. It actually took a lot of human judgment to figure out what was best.
Right, and I guess as a suburban user, I don't think about that much. My stuff just works, but being in a really radio dense environment like New York City, that is definitely a unique challenge. And just building also on something that you mentioned there, talking about having the human capacity and really relying on the human element. My colleague Jane Coffin likes to talk about it's the human nets that build the net nets. And I think, for you and for everything I've read about New York City Mesh, that really rings true.
I think it's very true for the last mile provider. I mean, so much of our work is in the field, and that we have to be present. We have to be there to be able to do a lot of the maintenance, particularly in the wireless environment, I think.
Yeah, and a lockdown and a pandemic sort of makes it a little bit more challenging to accomplish.
Absolutely.
But it's good to see that your subscribers are willing to share their knowledge and their experience with others.
Right, absolutely.
To help you get the job done.
That's the benefit that we have of being a community network. We're inclusive of everyone. We're not kind of providing a customer service in many ways. We try to increase tech knowledge across the board because we actually understand that our network is more resilient when skills and knowledge are shared across the user base. So the more informed of users that we have on our network, the more resilient our network ultimately is.
Absolutely.
Yeah.
And Jim, can you speak to the IXP industry and Nenix?
So one of the challenges that I saw across the ISP industry, as well as retail ISPs, was getting circuits delivered and capacity increases. There were a lot of IXs that waived port charges, and basically because this was an emergency, they said, if you need bandwidth, just tell us and we will give it to you and we will sort out the billing later. And there was a lot of very fast new capacity added in terms of additional ports or upgrades to the next level speed. I also saw a lot of the telcos doing things they have never, ever been able to do before, where they were turning around circuits that would normally take weeks or months, and they were doing them in a matter of days because everyone really understood that it was an emergency. Some of the retail ISPs were caught short without enough transit capacity, so there was a lot of additional transit orders. And definitely there were some new entrants into the world of peering. One of the things I wanted to point out that's still a problem is there's still insufficient peering, particularly when it comes to corporate VPN traffic versus home traffic. There's still way too many instances where your VPN traffic back to your office, and a lot of people still have to do that. They're not all in the cloud. That traffic sometimes is going hundreds of miles or thousands of miles, tromboning out of the next major market because that's where the two entities peer. So more local peering, please.
And what's the impact of the trombone routing there?
Increased latency, more packet loss, slower VPN experience. I mean, people have adjusted and have, gotten used to working from home primarily, and there's still a lot of people that are. And as everyone says, this is the new normal. Yep. But if there was more peering, I think the VPN experience would be a lot nicer.
Great, cool. And then just to close it out, talking about the future, building on the points we've just made, do you feel your organizations and your infrastructure is sufficiently resilient in order to capably handle that next unexpected surge in traffic? Again, as a CDN provider, Jana, the answer there is probably yes. But and I think one final question of, is there a key lesson from the experiences in your organization over the last few months that you're willing to share with the industry and your industry colleagues? So Scott, we'll start with you.
Sure, absolutely. I'd say, our network, we scrape by as much as humanly possible because our job, we're not only do we have a shoestring budget, but we also our goal is to have a neutral network. And so we're not out here throttling data or anything like that. So we're trying to get everything we can out the door as quickly as possible with respect to bandwidth. So with respect to our network and how it holds up, there were a lot of challenges. We're in the process right now of installing a lot better equipment, larger antennas, things like that, and doing a lot of the back-end maintenance work. We learned a lot from the process. And but with respect to lessons learned, I think two lessons really kind of came to mind in thinking about this. The first is the importance of investing in human capacity, and that's what I was mentioning earlier is incredibly important for us. And that's what the back end of so much of this is still run by network engineers and people doing the work on the ground. And the other, I guess, is really thinking that though remote is all the rage, and many of us, including myself, are all working from home these days, local really is important. And we realized that, and that we had to have people in the field local to where the problems existed. We couldn't have somebody, for us, taking subway across town wasn't a possibility. So we had to have groups of volunteers or people who are able to walk up the block or do something like that to be able to do that kind of maintenance. And I think also, it gets to Jim's point earlier, I think also local is very true with respect to peering. With the traffic going over our network, if we can keep a maximum amount of that traffic locally within the network or directly with somebody we're peering with in a local exchange, that makes a huge difference for end users. So not only kind of having people and capacity local, but also traffic local. Absolutely.
And Jim?
I'll agree totally with Scott on the people and in general. Challenges is, lessons learned. Access to facilities is very important and was a challenge during COVID for different reasons than some of Scott's reasons. A lot of the facilities were essentially unmanned and had severely restricted access, and access was essentially by appointment only. A lot of data center facilities, and I know this affected other IXs, those data centers maybe had one technician, and so getting remote hands requests was basically impossible, or you had a very long wait. So those are, issues for the future. And always, of course, more capacity, more peering, always going to say more peering.
And hopefully a lot of organizations now are revisiting their disaster recovery plans and their disaster,
business continuity.
Thank you. The business DRBC plans and incorporating things like what happens when there's only one guy in the data center.
Yeah.
What happens when we can't get into our data center? And maybe that's when we start relying more on CDN services. So Jana, we'll close it out with you.
So basically, like you said, as a CDN, having a CDN helps, right? I mean, so my heart goes out to those who had to scale their services overnight, but didn't have that to back them up. But so in terms of looking to the future, we've we've been investing in infrastructure, in capacity. We recently announced that we reached 100 terabits of serving capacity, and more broadly around the internet. We want to build a technology that can help us move forward like this. So we're investing in technologies like Quick, various things that can actually help us move into the next level of internet use, so to speak, and to manage these things. In terms of the lessons learned, I have to say that there's something resonates with me when I heard Jim talk about how people stepped up to do stuff right here during these times. So we just a very quick prelude is that we dug into the data that I showed you earlier to see if different communities were getting affected disproportionately. Specifically within the US, we tried to dig in and see if poorer communities were getting more affected than richer communities. And the way we did this, we looked at five-digit zip codes. We looked at the average income from IRS data, and we correlated that with delivery rate to those particular zip codes. And while we didn't see a big difference in how much they were affected, what we found was quite stark in that we found that across the board, even before pre-COVID, delivery rates were completely striated. Like, the richest neighborhoods got the highest delivery rates and the poorest neighborhoods got the lowest delivery rates. And it was perfectly stratified. We had 5 levels that we classified the 5-digit zip codes into, and we got 5 curves of delivery rates. And that was just very stark. The really cool thing is that operators have stepped up. They did step up. So Comcast and Cox Communications, I'll call them out because they did something really good here. They came out and they offered the Internet Basics program for free for a while, and they also increased the bandwidth of those programs, and that actually showed in our data. We saw these striations, like, we had these 5 lines, and the bottom 2 sort of went up, and the gap sort of disappeared for those ISPs at least. So the lesson here is that we can continue doing this. There is a digital divide. We know that there's disproportionate people who are getting disproportionately affected, and that we as a community can actually step up and do something here. We can take that lesson out of this.
Right. Oh, absolutely. Absolutely. I think that's a great point to end on. I think the internet has remained resilient thanks to the work of CDNs and last mile providers and IXPs. I think that where we need to focus on improving the resilience is by closing that digital divide. It's going to require a lot of work, a lot of investment, and it's going to require a lot of investment not only in hardware and in bandwidth, but also in human capacity, like Jim and Scott said, having the right people in the right place at the right time. So I want to thank Jim and Scott and Jana for participating in the panel today. I want to thank the team at ThousandEyes for having us, and turn it back to Archana and Angelique.
Thanks, David. That was great. In particular, the discussion around access and really paying attention to that, in particular because, as Jana mentioned, like some of these trends that they were seeing existed pre-COVID, and even, afterwards. And there were some providers who stepped up. But if anybody is interested in learning more about this, isn't that part of some of the work that the Internet Society is involved in?
Absolutely, yeah. We do a lot of work around both community networks, helping to foster and to build community networks around the world, as well as shepherding IXP deployments in various locations, trying to help keep that traffic local. So the Internet Society website has a lot of information on both project areas.
Great. And hopefully you and some of the guests can stick around for questions at the end. There was a lot of really interesting topics you guys brought up. And thank you again, David.
Sure, you're welcome. Thanks for having me. And
next up, we have a talk, really interesting. This is on game delivery. So we have Bill Wanuka, who's VP of Global Internet and Content Delivery Services at CenturyLink. He leads a group of product managers, and he's responsible for CenturyLink's internet access, content delivery network, as well as broadcast transport services. And the name of his talk is Game On. So we're really excited to talk about the challenges that you guys rose to in delivering streaming gaming.
Well, thanks for the opportunity to come on and talk about what we did. I'd suggest that many of our peers in the CDN space undertook the same activities and actions that we were asked to. So, as much as this is about what we at CenturyLink needed to do in order to, I think, be good stewards of performance through COVID, it's actions that our top competitors like Akamai and Fastly have taken through that process. Go to the next slide, please. One more. Okay, well, we sort of had a pretty interesting confluence of events here. The gaming industry has been an industry in change for quite some time, and it's no stranger to disruption. And I think the disruption we've seen over the last several years is that free-to-play and free-to-all games have become a very popular way to increase the user base, and then monetization is generally driven through other means rather than having a paywall to enter the game. What changed this year is that these concepts started to enter the business of what I would call very traditional AAA games. And those are games where quite a bit of money is spent on the art and the music and the distribution and the marketing of these games. So AAA games, might be a Call of Duty as an example, or a Grand Theft Auto, for example. One of the things that I think has really changed for the business is that as disruptors have come and launched, free-to-play games and free-to-all games in this space, AAA life cycles themselves can be extended with a simple value proposition, and that offer is free. And so for those of us that have never wanted to, spend the money to get through the paywall, typically about $40 to $50 for a AAA title, this is, created an opportunity for the market to really open up and encourage more game players. In fact, you can imagine a scenario where maybe my best friend and I are saying, hey, I just discovered this game online. We've been wanting to play this for a long time. I want to play against you. Let's go download it, and then we'll play as soon as it's finished downloading. Well, that value proposition diminishes pretty fast if the consumer experience is diminished when free does not equal fast. And even worse, potentially, my best friend may have been left behind and might have gone to join the game to play with some other friends, and that would then start to drive a bit of a relationship issue for us, in that I've picked up and started to play games with another group of people who are able to download it fast enough. And it's kind of a simple analogy, but I think it's it's very real, and it's very real to gamers, and it's very real to consumers that they need to be able to receive content when they're asking for it. Now, a lot of what's happening with game downloads too, to keep in mind, is that there are a number of patches, and the platforms themselves tend to pick up the updates to those games, without human interaction. So there's an element to this that is, let's go get the game and let's play it now. There's also an element to this that there's unmanned, IoTs essentially downloading, a fair amount of the game traffic that we see on a regular basis. So essentially, the global pandemic is, I think we've talked about this ad nauseum, but it's profoundly altered how we work, and it's increased the global economy's dependence on sustaining high levels of internet performance. So if you would go to the next slide, please. My idea of humor here is that when free AAA gaming meets the global pandemic, it's as if an irresistible force. We're meeting an immovable object, and the result is something that I think it's hard and difficult for every network to deal with, whether you're a CDN or an ISP or a transit provider, or you have a different angle on on a private network space that you're trying to manage. If we go to the next slide, please. High peak to mean peak ratios drive what we call regrettable costs. I won't give you the specific time frame here, but you definitely see a COVID curve, and you definitely see sort of the frequency of what large gaming events tend to look like over a period of a couple months. And those large events tend to happen very infrequently. They become an outlier in your network performance that you need to solve for. Carrying enough headroom to accommodate all of that peak traffic is expensive. And by regrettable, what we mean is that the time in between the peaks, you're not getting the advantages of having spent that money or having put that capacity into place. And so, when you think about the fact that these very, very large game spikes are infrequent, it just makes the problem significantly more difficult to deal with. Certainly is a call out to do something more thoughtful. If you go to the next slide, please. Forward, yeah, thank you. And so governments weren't shy as we went into COVID. They were aware of the risk that that large game downloads create for user experience. And a number of regulators, informally or formally, reached out during this period of time to really the full ecosystem of game distributors. So the people who have the platforms and deliver games for game developers. You can think of the large ones being companies like Sony or Microsoft or Electronic Arts or Valve or Activision Blizzard. And the tendency in this space is, to be very marketing led. So as a new game becomes available, the desire to get that game into consumers' hands as quickly as possible is an absolute business driver and business requirement for the revenue side of that business. Similarly, getting patches out quickly and ensuring that players have similar experiences in stable platforms and are able to engage at the same time. These are all really, really highly important aspects of running a game distribution business. And the game developers and the game distributors have long used specific days during the week for large events. And so in the last slide that you saw, you would have noted most likely that the peaks would occur somewhat infrequently, but the big day game download day on the internet tends to be on Tuesday at about 11 p.m. Pacific time. And typically what will happen is those games will be launched across the globe at that time. So as that patch or that new binary is available, it's put into the distribution platform and then pushed out to as many devices and as many users as possible in a single window globally. So what the governments came back and said is, look, where feasible, we should be using off-peak hours to accommodate large downloads. And that should be scheduled from midnight to 8 a.m. And if you're at 11 p.m. on the West Coast of the US, you've probably just about made it out of the primetime window peak for video traffic and OTT and other types of consumer traffic. But you're hitting business hours in Asia Pac, and you're hitting the start of the business day in Europe. So I think the ask here was really start to plan to roll those releases into an off-peak window so that we're not in disrupting business hour traffic, which has become so much more important. If that's not impossible, they also asked that we avoid peak times of 5 p.m. to 11 p.m. This would be when I think OTT typically sees its big liftoff every day, locally in each region. And I think that the entertainment and use of the internet for entertainment and for speaking with your family and those things were heavily considered there. The ideas and suggestions about rolling downloads, phasing of downloads, rate limiting and spreading download traffic. I think, I've kind of covered the main, concerns there. Rolling downloads and phasing could absolutely be accomplished, but not without a change in the way that the industry views its opportunity and its need to get content to consumers quickly. So the final piece, advanced warning of significant releases and updates to ensure preparedness. This is a practice that I believe every CDN, works with their game download customers to achieve. But even, there are times when our customers on the operations side are not necessarily privy to the exact release date, or that release date is being treated as confidential and need to know. And so, definitely leaning into an area here where our customers and the people we work with directly may not be privy to the actual dates themselves. So some real challenges in this. I would say, there was a lot of dialogue that was both public and private, and there was a great opportunity to interact with customers and with some of our peers as well. Now, from a COVID standpoint, we absolutely saw the same lift in traffic across our IP backbone that's been described here, about a 30 to 50% lift on daily peak traffic. And we worked very closely with ISPs to ensure that capacity upgrades that were going into place were accelerated, and that where we expected to see traffic congest, that we would pull forward on our planning budgets and co-invest. So we took those actions all across the globe with our ISP partners, and it certainly helped. But again, it's hard to plan for these extreme peak events. So we had to take additional measures, and I'd like you to go to the next slide, please. One more. I'll call this a short-term solution, and apologize here. There's a little bit of a misnomer on this slide. This is really meant to be a kill switch methodology, not a DNS kill switch methodology. But the idea here is that your HTTP servers, or whatever your responding device is going to return 5xx request errors, and that you will use those content not available errors to slow down the rate at which you're passing traffic back to the clients. So there's a real risk here, which is that the clients themselves will build up a very large retry request rate, in addition to the steady state demand, and that could create an even higher demand scenario once you remove the methodology of issuing a percentage of your total traffic of 500 errors. I think the other real problem with this potential methodology here is that it's inelegant, potentially, and would cause unexpected client behaviors that would result in errors. Certainly for any user traffic, that could be a real challenge to user experience, and it could have unexpected consequences on other platform elements, like a set-top box or a gaming console or a PC that's downloading the software. So what I've actually demonstrated in the slide is a use case that we observed in testing. What you see here, and this is testing in live with reduction in traffic. What you see here is a initial peak towards the middle of the slide to the left of the red circle. And then you see the effect of the kill switch on the traffic. So essentially discarding a percentage of traffic to maintain a traffic level that's comfortable, based on the capacity planning that goes into the network and the interconnections and the server side. And as soon as that kill switch is removed, you see that the actual spike that includes demand from clients that have been retrying goes up even higher. So this is I think a fairly crude methodology. We opted to work on a slightly more elegant methodology, and if you would go to the next slide, I'll talk through that one. I call this TCP session rate limiting. It's using TCP max response rates to reduce session throughput for your highest bit rate clients, thereby reducing the overall peak traffic throughput. There's a real risk here that your sessions could stack, and you'd see sort of a similar situation to what you saw on the last slide, where the actual demand from servicing more sessions simultaneously, creates resource consumption challenges in the serving infrastructure. And again, I think this had the potential to have inelegant or unpredictable client behavior, but it had a number of things that were right about it. The first is that in the world of gaming, if any of you have spent any time there at all, from a user standpoint, there's a lot of focus on what's fair, and having an advantage in gaming that you didn't deserve because of your skills or because of your accomplishments is viewed to be pretty negative in that community. We do believe that dropping the top bit rates allows us to have a pretty precise control and targeted decrease of the peak traffic. So if you think of it this way, let's say that the average traffic in Great Britain were 30 megabits per second, and we said we wanted to accomplish a 25% reduction in overall peak traffic. We would then hypothetically go ahead and create a max response rate that would lead to a throughput of 22.5 being the top throughput, and we would essentially drop our top bit rate. what I wanted to show you here and demonstrate, this is real data. I've had to anonymize it pretty significantly. The effect would be on the client behavior in the blue line there. The client is going along swimmingly, getting up to 30 megabits per second, depending on network conditions and other variables in their environment. And that would be, as tested to a specific server asset on the CDN side. And at the point that the throttle would kick in, what you would see is that the bit rate would be capped at 22.5. So there you have sort of an average bit rate of 30 megs. And then for the period of time that the cap is applied, let's say that was during peak hours, during internet usage, or maybe it's not during off-peak, but during business hours. These throttles can be applied and have a really precise effect on exactly how fast the web server would allow the client to receive data. In our case, this required us to do some development, which we were able to do during the period, and able to actually, canary soak that and get confident and comfortable that we were able to deploy with multiple major customers during the event. The net impact of this, however, is observed below from a market behavior standpoint. What I'm demonstrating there is 2 days of peak traffic. And in the line below, there's those 2 lines there. You see one of the lines is having a much smaller peak. We actually tested this traffic in the market that has the higher peak, and where I've circled in red, you'll observe that those 2 markets actually came very close together in terms of peak traffic, and we achieved about a 15% improvement at that point. After the 2 peaks in the middle, you will see that the 2 markets sort of return to the ratio of traffic that they were each serving before. So on the left, both markets are uncapped. In the middle, one of the markets, the larger of the 2, is capped, and the 2 peaks come much closer together. And then we applied the methodology back to the smaller market, and you see that the ratio stays the same between the 2. So if you go to the next slide, please. So just kind of a quick summary from our perspective. There's 2 viable methodologies here, and CDNs and ISPs tend to be belt and suspenders guys. I would say that the TCP session rate limiting allowed us to use very gentle and non-user observed condition that effectively gave us a very fine control over how much traffic one of our gaming customers would want to send. So they were able to tell us, this is where I want to be in this market, either on a throughput standpoint or peak standpoint. And given the Lua scripting nature of our edge, we were able to just go ahead and set up rules that allowed us to apply those rules whenever the customer would want to have them implemented. Now, I'll say not every customer wanted to do these things the same way or felt the same about every market, but it certainly was simple for them to use. There was no development required on their side. From my standpoint, the effectiveness was high. We saw incredibly tight tolerances to the targets that we set once we had kind of vetted the hypothesis, and the network risk was low. We were essentially, I think, very worried at the beginning, but after several days of canary soaking and going fairly slow and watching under conditions that were changing constantly, came to the conclusion that this wasn't creating CPU bottlenecking or any of the other server resources that might have been congested by trying to tie up more resources. Ultimately, again, this is the kill switch. The 500 errors are essentially what we're talking about here, just to avoid any confusion. Time to effect is typically was on the order of about 15 minutes. So if you wanted to make a change immediately, it wasn't an easy thing to do. You needed to be a bit ahead of it. There was observed user experience issues. I think, again, this was a very simple thing for customers to use, but the effectiveness was essentially only medium. To a large extent, you really can't control how much traffic you're receiving as a CDN serving for a customer. And so there's always this risk that the demand is infinite and you're eventually going to run out of resources. And I think that this methodology creates a little more risk there. It's just a little less elegant, and then it does present a higher network risk. So at the end of the day, we've actually adopted both methodologies, but the TCP session rate limiting is the one that we feel has the best results for the customer. And then I think you would keep a kill switch in place in case you had a very dark day on the internet. You do have some additional tools in your bag. I had just a couple more comments. These were short-term solutions for us. If you could go forward to the next slide. We have been working on a long-term solution, and this is something that you may have seen. We announced that we acquired StreamRoot in 2019. They are a peer-assisted mesh delivery company. So they specifically work with CDNs, and it is an open CDN technology. They work with all CDNs, not just ours. So they've worked very hard to be, I think, easy for a customer to integrate with CDN in any multi-CDN strategy they have. Peer Assist has started to gain traction in the video space, in particular in Europe, where we've got several announced large customers that are, fairly popular regional broadcasters for that area. What we've seen over time is that hybrid CDN and Peer Assist can deliver elastic scale. That's not possible by just using the physical assets in a north-south relationship between a CDN and an ISP. And that they're also incredibly effective at improving user experience metrics for hard-to-reach geographies, and effective routing for ISPs to manage it. The technology takes more advantage of the east-west capacity that's available downstream in the ISP's network, and generally speaking, we've received very positive feedback from ISPs that this technology is enabling them to avoid those regrettable upgrades that we showed in the first slide. So I've got a little bit of data to just kind of back that up here. If you would go to the next slide, please. In a mesh delivery use case, and this is a real customer's traffic. Here's a large-sized broadcaster in Europe with traffic identified during COVID period. This is specifically during the French president's address to the nation regarding the stay-at-home orders. And during the spike in traffic, we were able to achieve a 70% east-west offload, if you will. So peer-assisted offload, where the devices that our customers have their players running, and where they've taken our code and put it in their players, those devices were able to offload the north-south traffic, which is what you see in red, which is CDN to ISP traffic. We're able to offload that and serve more of it from within the ISP's borders. So less dependency on interconnection and peering. And again, for an event that was essentially 3 times the 95th percentile. So if you look at the second slide on the number of users that were simultaneously viewing the event, you'll see that not just the peak to mean peak, but the peak to 95th percentile was 300% here. That's just not something any ISP can afford to plan for. And so, given the importance of this communication to the nation, we felt like this is technology that really enabled a better way for the government to communicate with the citizens. And what you see at the bottom there is the change in buffer rates. And so I guess the irony in all of this is that at the highest spike that we saw with this particular customer during this period of time, they were actually achieving the best and lowest rebuffer rates that they measure. So if you think about it, it makes a little bit of sense. The more peak concurrency there is for a object or a video or a piece of software, the more devices there are that are trying to retrieve that, the more those devices can be efficient and download less of the traffic from north-south and increase the amount of traffic that goes east-west inside of the ISP's backbone behind the peering. I guess the final slide here, and the punchline for me, if you go one further, is that when we acquired StreamRoot, the first thing that I worked on with the founders, Pierre-Louis and the team over there, was to ensure that we had the right number of software developers in the business case. And we really focused on the idea that gaming was if not as important, a market to put this technology into, that the technology would have to be customized. So we've accelerated our game downloader development, and that will include an off-the-shelf download manager that a gaming company could deploy, and an SDK inside of that downloader. All of this is being ported into C++, and we're working on making these libraries available on the native platforms as well, so that developers can find these APIs and find this capability within platform devices themselves. So I'm anticipating a release of the product offering in 2021. But we think that it's going to be a very, very helpful software trick to add to the mix here. And we'll be spending a lot of time working with the downstream ISPs and with our peers to ensure that they understand what the technology is, and ultimately allowing them to customize traffic flows between peers within their network. So ensuring that they have fine-grained controls on an IP prefix layer, so that they're able to actually guide the traffic within their network themselves, and have the ability to influence which peers serve across which IP prefixes. So that's kind of the end of my discussion here. But it's been a crazy time. We've seen a lot of great cooperation between customers and ISPs and our partners. And just want to thank ThousandEyes for having us on today.
Thank you so much, Bill, for being there. It's funny, like you think everything works, so it's so nice to kind of hear behind the scenes what happens. So thanks for sharing that. I just think the DNS kill switch that you mentioned, so not a misnomer. So it's kind of funny and interesting. So thank you so much. We are right up on time, so we are gonna introduce our next speaker here. We have Marcel. Marcel's gonna talk to us about taming Anycast in the wild internet. And Marcel completed his computer science and PhD at Northwestern in 2016. And his research has been on enabling, additional channels of communication in existing networks and improving network performance. And since then, he's worked as a research scientist at Verizon Digital Media, where he has further explored transport layer optimizations, large-scale management strategies, and cache optimizations. With that, Marcel, thanks for being here.
Yeah, thank you so much for the intro. So today I'll be telling a little bit about a system we built for managing Anycast on the internet. So we call this taming Anycast in the wild internet, and with the undernote here, under duress, because we're going to talk a little bit about some of the challenges that we faced with the COVID-19 lockdowns. I do want to give credit where it's due here. A lot of this work was actually originally done by my intern from a few years back, Stephen McQuiston, who can be found at the University of Glasgow these days, and our colleague at the time from the traffic management team, Sri Priyanka Uppu. So this work actually originally appeared at IMC 2020, the Internet Measurement Conference, but this has some relevant COVID-19 updates. So we'll go to the next slide and dive in here. So just to give a little bit of context on the sort of environment that we'll be talking about today. So I'm from the Verizon media platform. You may know us by one of our older monikers, the Verizon Digital Media Services, or the Edgecast CDN. So we have a big multi-tenant CDN, right? We're not just an internal Verizon service, but we do regular business-to-business CDN services, and we're global, right? We're spread all over the world. And one of the really interesting features that our network has is a large number of interconnects, right? We have these points of presence, and each point of presence is connected to many other networks. And that's actually going to be sort of the interesting thing, right? It's gonna create a lot of opportunity for us to do fast and efficient delivery, but is also going to create some challenges that we sort of have a proposed solution for. So if we hop over to the next slide. So our CDN today uses Anycast for delivery. So this is in contrast to a sort of DNS-based load balancer. There's a few different ways you could design such a system, but right, DNS is a very common one where when a user wants to request content from the CDN, they resolve a name which has a load balancer sitting behind it, and then that makes a decision about which server to send you to. And that works very well for a lot of setups. But what we use instead is something called BGP Anycast. So what we do here is from each of our points of presence, which I have a sort of little sample here labeled as these blue squares, we announce the same IP prefix, right? And the idea is that once we've multi-homed, right, those announcements will propagate out into BGP, right? And when a user wants to connect to our network, right, they send a request to one of those addresses. And rather than making an explicit choice about where they should go, the network decides for us, right? Those routers in the middle will do IP routing as normal. They'll use their BGP tables and they'll choose one of these sites. Now, this is really handy. It gives us a lot for free. For example, we don't have to make any sort of critical path decisions on where to send users, right? We don't have to have that load balancer hiding behind the DNS resolution. And because BGP prefers shortest paths, this mostly works out. So most of these green dots, which sort of represent clients, go to the sort of closest blue square, closest for some definition of network closeness. Now, this also buys us a few resiliency features, right? If we need to take a site down, instead of having to drain connections slowly over a long time, what we can do is we can withdraw the BGP announcements, right? Which will cause the BGP tables to sort of smooth out, and traffic will get sent to other locations, right? This makes certain management tasks a lot easier. But we'll see that because we're depending on the network to make decisions, it sometimes doesn't do what we want. So if we hop to the next slide, you can see an example of that. So here is kind of this is a little bit reductive, but I think it illustrates the point well. On the left, we have a little blue square that symbolizes a point of presence in California. On the right, we have that yellow square, which is a point of presence in Colorado. And then the circles here are end users. And in this example, they come from two different ISPs, the purple ISP and the green ISP. And for whatever reason, when they send connections into the network, right, they're sending us HTTP requests, and they're getting routed through regular IP routing. They're getting sent to that California location. Now, functionally, that's okay, right? They're getting their content, everything's sort of flowing properly, but they're going kind of far away, which means they're potentially paying some latency penalty, right? It may take, say, 35 to 45 milliseconds to get that content from California, which is starting to get into the range where it's user detectable and might start to degrade their experience a little bit. But even worse, there's a better choice, right? We can see that there's that point of presence right there in Colorado that they could be connecting to instead. So what I want to do is I want to break down this scenario a little bit, and we'll look at one of the potential causes of this and what we can do about it. So if we hop to the next slide. So here's kind of a simplified explanation of what might have happened there. And there's kind of a lot of arrows here, so we'll walk through it carefully. So on the left, we have site 1, which we can sort of pretend is our California site in the previous slide. And on the right, we have site 2, which we can sort of pretend is that Colorado site in the previous slide, right? And so those are our 2 points of presence, and they're announcing the same Anycast address, right? And then we have this gray circle in the middle, which represents the end user, and he lives inside some ISP, which we're going to label ASB. Now, it could be that ASB and ASA both buy connectivity from some provider, Transit Z, right? And this is going to be a customer-provider relationship, right? Both ASA and ASB are going to pay Transit Z for this connectivity. And that's a very usual way to get connectivity on the internet, right? That's kind of the model. It's hierarchical and has this kind of relationship. But it might also be that ASB has another connection through another network, which we're going to label peer X. And it might be that this peer X is not one of these customer-provider relationships, but instead is a peer relationship. And it might be that ASB has a sort of settlement-free peering arrangement with this peer, which is to say they've agreed to carry each other's traffic without cost. And it might be that actually ASA has the same relationship with that peer X, but in California. So what's going to happen is ASB is going to have this packet from his user, right, that SYN packet to start the connection. And he's going to look at his routing tables, and he's going to have to make a decision. And he's going to say, should I send this to Transit Z or should I send it to peer X, right? Both of these are valid routes for reaching ASA. And probably what he's going to do is he's going to say, well, these routes are the same length, so I have to break a tie. And if I have to break a tie, I'm going to go with the cheaper one, right? I'll send it to peer X where I don't have to pay for it, and everybody will be happy. And he's sort of not wrong to make that decision, right? That's a fine configuration for a network. So he'll send that packet to peer X, who will send it along to site 1, who will get the request and service it, but at some latency penalty. So what ended up happening here is the request went to site 1 instead of the much closer site 2 due to some policy that ASB had cooked into their network. And again, it's not that ASB made a mistake, but I think the scary thing from the perspective of the CDN is that that's policy we can't necessarily see, right? We don't necessarily know what choices ASB is going to make, right? And it's sometimes not until it happens that we know these are going on at all. Now, there's a couple of different remediations you could consider here, right? There's sort of a lot of classic sort of network engineering tricks you could do. For example, the most straightforward perhaps is that ASA could try and add peering with peer X at site 2, right? Make this a sort of non-issue. There are lots of reasons why that might not be tenable. Maybe they're not in the right data center or things like that. Maybe peer X's router is full at site 2, so it's just physically not an option. Another old-fashioned technique could be to call up ASB on the phone and say, hey, you guys are making a routing decision that's hurting your customers. Maybe we can work something out, right? And maybe we can get them to adjust that policy. But not all of these are sort of scalable, right? It works if this happens once, but what if it happens a lot? So next slide, please. So what I want to do is I want to take a little step back, and I want to think about what makes this kind of scenario so tricky to deal with in real life. Next slide, please. And the issue really comes down to two categories of networks, right? And these are a very qualitative feature, or that maybe there's not a super tight description for, but I think they sort of convey the nature of the problem well. Which is the first is there's a type of network that I'm going to call few provider networks, and this is actually what most networks in the internet are, right? They have maybe one transit provider and a handful of peers. And if they're lucky enough to maybe be connected to an IXP, they maybe pick up tens of peers at that IXP or hundreds in some cases, right? So, but generally speaking, they have a small number of next hops available to them. On the other hand, on the next slide, we can see another type of network, which I call many provider networks. And these are networks where you have many transit providers and many more peers. Right? And if you run an Anycast network, you might have many sites where you have many transit providers and many peers at each of those sites. And when you're in this kind of situation, right, you don't necessarily have the ability to sort of suss out every interaction that'll occur between these peers. Right? As soon as you're talking about hundreds of peers, or as we saw in that initial slide, 5,000 interconnects, it suddenly becomes extremely difficult to figure out who has what relationships with who and what sorts of policies they might have, right? You can make some guesses about who's a provider and who's a peer, but it becomes very tricky very quickly. And next slide, please. So this is just to give a sense that this is a real thing, not just a construct I invented. So one of the things we looked at is we tried to understand how different Anycast networks compared in terms of the number of providers. So what we considered here is the number of clearly available next hops in public routing information. So this comes from the route tables we can collect from the Route Views project. And here what we looked at is we looked at the DNS root letters, the A through M root letters, which are running Anycast networks. We looked at our own CDN, which is labeled CDN, and we looked at a popular open recursive resolver that we labeled GDNS that also runs on Anycast. And what we saw is from this publicly visible data, which I do want to say is certainly not all connections, but is some subset of them, we see two clear categories emerge, right? There's the category which is largely on the left, where we see the number of peers is very low, right? In some cases, it's sort of only one. In some, it's a handful. And then we see a category where there are many provider networks, right? Hundreds in some cases. And this suggests us that this is indeed a real distinction, right? That there are sort of two different administrative configurations that are going to have these very real performance impacts. Next slide, please. So what is an Anycast network to do, right? How are you going to figure out how to configure your network so you can avoid these kinds of issues, right? Where where traffic is choosing some peer due to some policy and choosing a suboptimal Anycast site. What you can do is you can kind of think about the situation as a matrix, right? Along the x-axis, we have our Anycast sites, and along the y-axis, we have all of our providers. And then you can say for each site and for each provider available at that site, should we announce our Anycast blocks out to that provider, right? And you can kind of think of this as a big binary matrix, right? You can switch each one on and off, and they may have different performance outcomes when you do that. So next slide, please. So that's sort of the overall thing. But an important thing to keep in mind here, and I think something that makes this challenge a little bit different than some of the other sort of popular traffic engineering questions that have been raised recently, is that Anycast is ultimately a question of inbound, right? We get a request from a client, which is going to be routed to an Anycast address, which is going to be small data, right? This is going to be an HTTP request on the order of bytes. And we're going to send a response back to that client's unicast address, right? And that's going to be a big response on the order of megabytes, perhaps, right? If you imagine streaming video, they're sending many of these small requests and they're getting very large responses. And so what this does is it means that once a request arrives, we need to answer it, and we need to make sure that we have the capacity to answer it at a particular location. So that means when we're changing around these Anycast configurations, we're changing how traffic is coming into our network, which in turn changes how we can push it out of our network. And that really makes things complicated. The analogy I really like for this is it's kind of like driving a car while looking in the rear view mirror. You have to kind of remember, like, you turn the steering wheel this way and the car is going to go the opposite way, right? So it makes it a little more complex than just traditional egress traffic steering. Next slide, please. So the first thing I want to look at, though, is how much does it actually matter, right? This sort of California example was maybe a little bit contrived, right? Maybe I picked that because it had a nice picture on the slides. So what we wanted to do is on the next slide, we wanted to take a look at how we could actually measure this, right? And understand what impacts we had from these kinds of configurations. So what we did is at each of our Anycast sites, we defined two groups of providers. The first is what we're going to call the control group, right? And this is going to consist of just our transit providers. This is kind of the most conservative set you could choose, right? These are the providers you need for full connectivity to the internet, right? So that's our control group. And then we're going to define a second group, which we're going to call the experiment or the experimental group, which is going to be both those transit providers and all of our peers at that location. And what we're going to do is we're going to take two Anycast addresses, and these are special test blocks that we can manipulate without impacting customer traffic. And we're going to announce one of them from to just the control group, and the other to just the experimental group, or well, to everybody, basically. Next slide. And once we have these configurations set up, we're going to do some measurements. And to this end, we're going to use the RIPE Atlas distributed measurement platform. For those unfamiliar, this is a program set up by the RIPE NCC out of Amsterdam, and it consists of about 10,000 globally distributed devices. They're these little hockey puck size measurement probes that you can put in your house. I have one in my living room. And once you participate in the program, you can run experiments from these different probes. For example, you can do pings and trace routes and some limited HTTP gets. So that's what we're going to use for our measurements here. Excuse me. It's worth noting that the measurements here aren't exclusive to RIPE. You could actually use any platform in which you can do trace routes. The key is we have to simulate that user experience. We have to be able to measure from outside the network in to us. And for some convoluted technical reasons, we need to be able to do trace routes. So on the next slide, I sort of show what we do then is we measure these control and experimental groups using these probes. And then we group the probes together, right? Each individual probe might be a little bit noisy, right? Somebody might be downloading game updates, for example, on their home internet, which will maybe cause a little bit of cross traffic. So what we do is we group the probes by AS and geolocation, which is to say by ISP and their physical location, either country or state in the United States. Next slide, please. So what we see is once we measure from all these probes and we measure these two configurations and we look at the difference in round trip time performance, right? And on the x-axis here, we have the relative change between that same probe's performance with the control group versus the experiment group. And on the y-axis, we have the CDF of groups. So what we can see is that for about 60% of those groups, they saw improvement, right? Things got better. And that's consistent with our expectations for how peering works. You add more peers, you get better connectivity, right? You maybe have more shorter paths, so things are better. So we were glad to see that 60% improvement. On the other hand, about 40% of probe groups did not get better. In fact, some of them got quite a bit worse, which suggests that actually this concern about these types of policy scenarios like we saw before are valid, right? And we do need to be careful. We can't just announce to everybody and hope for the best, right? This is going to require some careful work. Next slide, please. So this is just an example to show you how things can sometimes get a little bit out of control. So this is an incident we had a couple years back when we tried to turn up a new provider in a location, and there was a small misconfiguration in how that happened. And as soon as we started announcing that to that provider, we started pulling in clients from all over the world, which was not the intended effect. So the red dots here show you during the incident, and the black dots immediately before. Now, luckily, this triggered a couple of sort of circuit breakers that we have, so nothing bad happened here, but it was definitely scary and sort of goes to illustrate the danger of misconfigured Anycast in these cases. Next slide, please. So the last thing I want to talk about from the sort of defining the problem space is keeping in mind that there are pretty wildly different network volumes, right? Different ISPs have different numbers of users, and those users request different content from the CDN. And what that does is that can cause really uneven load. And that gets even worse when the Anycast behaves unpredictably. For example, in this little example I have here, ASB may, for reasons like we saw earlier, begin connecting to a faraway site. And that has the sort of round trip time performance implications, but it also means all those users under ASB are now connecting to site 2. And that's potentially putting a lot more fresh load on site 2, which may create its own problems, right? So this isn't just a question of round trip time performance, but actually of true traffic management, right? Of controlling traffic volumes. Next slide, please. So what I want to look at now is I want to take a little look at what's happening today, right? In particular, in light of the COVID-19 lockdowns and the impact that's had on the internet as a whole. So on the next slide, what I have is I have the number of requests taken from a single POP. Now, I've had to do a little bit of anonymization, so sorry about that. But what we have is the red line showing the request rate for a week in March, and the black line showing the request rate for a week in June. And we can see that this week over week difference is profound, right? We see about a 25% increase in total request count over this period, which is significant, right? I mean, as other speakers have talked about today, right, we have sort of planned organic growth, and then we have sudden growth. And this was firmly in the sudden category. On the next slide, we have the same point of presence for the same set of weeks, but here, instead of looking at the requests, we're looking at bandwidth. And here we see that the bandwidth out actually increased even more dramatically, right? Almost a 50% increase, right? And that's interesting because that means not only did we see similar, large increases, but we see that users are asking for larger files. This sort of is what we expect maybe as certain things like streaming, video streaming became even more popular, right? People are at home entertaining kids, things like that, which creates a certain traffic pattern. Another interesting thing, which you can see a little bit on this graph, is that the diurnal peaks widened a little bit, right? So we got busier earlier in the day, and that persisted a little bit later in the night. Next slide, please. Another interesting thing that changed dramatically is where traffic was coming from. Right. So here what we're looking at are what we call eyeball networks, right? Networks that have end users in them. So this is a handful of eyeballs at a single point of presence, right? Each line is a different ISP. And the y-axis here is sort of normalized to the pre-lockdown maximum. And what we can see is that over the month of March, the amount of requests coming from these eyeball networks increased dramatically, right? About 20% for some of these. And because many of these are sort of our largest source of traffic anyway, that's a pretty dramatic change. On the next slide, you can see that when we consider, we bump to the next slide, please. When we consider wireless providers, we actually see the opposite trend, right? And this makes sense, right? User mobility has decreased, right? People are hanging out at home. They're using their home internet instead of their wireless provider. So it's not a surprise that this dropped. But what this means is that our sort of traffic matrices have gotten a little bit scrambled, right? Places that were big sources of traffic before have decreased slightly, and other sources that were big sources before have increased slightly, or not slightly, dramatically. So on the next slide, what we can see is that these big changes are sort of swinging things around. We're moving a lot of weight on the internet. And because these were some of our biggest contributors, that means we're truly talking large volumes. And when we're doing all that, we need to know where traffic will go, right? If we're going to make changes in the network, we're going to add new peers, we're going to change our BGP announcements, we need to know what is going to happen, right? Otherwise, we risk breaking things, right? It's kind of like redlining your car, right? If you're pushing it really hard, you want to make sure that you know what's going to happen next. Next slide, please. So what do we do? What we're going to propose is a system called Daily Catch. So what Daily Catch does is it allows us to take snapshots of the behavior of different configurations. So for example, we can consider those control and experiment configurations that we saw before, right? We can measure how each one worked, and Daily Catch will allow us to compare them and tell us, A, what happened for different groups, so we can see who improved and who got worse, but we can also distill that into a combined score, which will allow us to make better decisions sort of on a large scale. So on the next slide, you can see sort of the workflow that Daily Catch has, right? We use, again, the RIPE Atlas platform, but again, any measurement platform with sufficient visibility will do. We send trace routes to our control and experiment groups. A lot of times our control group is our current production network, right? We want to compare how things are today, and our experiment group is a set of test blocks configured on sort of a proposed change. For example, a new provider or a shift in our policy. We do those measurements, and then we convert the round trip times that we measure into this weighted score. And we do this so that we can sort of easily compare them without having to look at relative differences all the time. We then weight these scores by the volume that we see coming from each of those networks, right? There are certain networks that are just a little bit more important, right? Eyeball networks with end users to them are critically important. Strange enterprise networks that don't actually provide that many requests to the CDN just don't matter as much. So we sort of weight them accordingly. And then we combine these scores with a simple sum. And this allows us to say, okay, did that experimental configuration result in better performance for more users? That is, did the sum go up or down? And the other thing we can do is we can look at individual groups and say, okay, with the experimental configuration, who got worse? And then we can try and understand why they got worse. Next slide, please. So if we want to return to this original example, we can imagine that, say, this scenario where these Colorado users are connecting to California is kind of our control configuration. Maybe that's what happens in production today. And we could consider some experimental configuration where perhaps we added peering with that peer X at our site in Denver, wherever that is exactly. And on the next slide, we might see what might happen with that experimental configuration. Right here, all those users are now connecting to the closer Anycast site, and as a result, are seeing improved performance, which would then result in an improved score. Next slide, please. So here's actually a pretty cool measurement we did using those original experiment and control configurations, where we saw that not only did some configurations make things better for different networks, but that actually the impacts are not uniform within the same network. So this is from a single residential ISP that we measured. And with one of the configurations, we saw some behavior, and then we considered the experimental configuration. And if you look at the dots here correspond to the right axis, the improvement or negative improvement in milliseconds. we can see that on the far right, the customers in Massachusetts and Colorado saw significant improvements in performance, but customers in New Mexico actually saw significantly degrading performance, right? And this was due to a convoluted set of routing choices. So we were able to see this, though, because the groupings clearly highlighted these differences. And that allowed us to dig in and address these directly while still pursuing the gains that we were able to achieve on the right there. Next slide, please. Another cool thing we can do with Daily Catch is we can consider snapshots over time. So instead of considering explicit configuration changes, we can look at how things change on a fixed configuration over time, right? And we can, for example, collect these snapshots every day and look at how performance has changed over the course of a month. And this is important because, as we saw, a lot of these ultimate behaviors are determined by choices that happen inside the network, outside of our control, which means that they may change arbitrarily. So by measuring over time, we can see when those happen, we can see when things degrade, and we can see specifically how they degraded on the group level, and we can address them more effectively and more quickly. Next slide, please. So overall, these many provider scenarios offered just a great deal of flexibility, right? We have more peers, we have more shorter paths, we have greater resiliency, right? Things are good. But it comes with significant challenges, right? If you want to run an Anycast network in this scenario, you're going to have to do a little bit of relationship inference, and you're going to have to manage volume, right? You're going to have to know which users are going to go where. And Daily Catch provides crucial understanding of these interactions without having to measure each one individually. So we've had it deployed for a couple of years now at this point, and we found it to be a very handy tool for addressing these types of challenges. So that's all I have today. Thanks very much to ThousandEyes and the folks for putting this on and having me. I think your mic might not be on, actually. Sorry.
No, thanks. Thanks, Marcel. I was just going to say this is a really interesting talk. You were talking about how in running a large Anycast network where it's sometimes hard to predict what the impact will be of some of the changes that you make. Looking at it continuously and kind of getting that real world visibility into what actually happens and what the impact is for users is just something that you just have to do on a continuous basis.
Yeah, exactly.
Yeah. And with Daily Catch, I assume this is sort of something you're again kind of looking at every single day and then kind of incorporating the.
Yeah, definitely. It's one of those where you pop the dashboard open in the morning and you look at it and you go, what happened there, right? And then you dig in. And you find that there was a big shift, and oftentimes you start to see those impacts elsewhere in the CDF performance.
Yeah, awesome, great. Well, we're running a little behind on time, so we're going to save questions for the end. Thank you again, Marcel. So up next, we have Roger Barranco from Akamai. Roger is the VP of Global Security Operations. Thanks for joining us. He was previously the VP of Service Delivery at Prolexic prior to the Akamai acquisition, and before that, he was the CTO and VP of Operations for Host.net. We're really excited to hear about some of the experiences that you've had over the last few months in terms of security. Thank you for joining us.
Yeah, thanks very much for this opportunity. I'm very passionate about this topic, but I'll talk fast at times intentionally so that we have time, hopefully, for questions and can get back on track. Next slide, please. Okay, so the items that I'm going to talk a little bit about today is SOC and NOC interoperation. Going to also share some threat research snippets, talk about different attacks that we've seen, and I really want to spend a little bit more time on what you can do to better position yourself to protect yourself from that day that, if you haven't experienced it yet, probably will come when you become a target of a malicious cyber actor out there. And then, like I said before, we'll have some Q&A time after that. Next, please. So when we talk about the SOC and the structure of the SOC, there's a lot of different layers in the team. Our security team is quite large. If you bring that down to just the people that focus on triage and actual detection mitigation type efforts, it's around 200 people globally. There we have 6 SOCs positioned around the world. We do that for the purpose of trying to get as close to our customers as possible. We don't have a follow the sun model with the exception of Japanese support. And we want to create personal relationships as best possible with our customers when there's a security event that they can need a little assistance with. So that front line is the triager. So they are highly available. As soon as that phone call comes in or that alert comes in, they follow a very strict run book that's negotiated in advance with the customer on what the customer's expectations are for engagement. So we have tight processes around that that says, hey, you know, for this type of alert, it's not that important to me. You can just email me. Or for this type of alert or scenario, please get me on the phone or page me or whatever that contact method happens to be. Some customers in certain situations will say, you know what, I trust you all, just mitigate that attack, do what you need to do. You don't have to proactively engage us. It's according to whatever that customer's change control expectations are along the way. But that front line of triagers gets a lot of information, just like I'm sure many people on the call also get a lot of information flowing their way from an alerting perspective. And they'll go through and categorize, and they're sitting physically near security specialists and networking specialists. And they'll, in parallel, engage the right resources to jump on the problem with them and communicating with the customer. A huge piece of it is just the monitoring aspect of it. When we talk about false positive rates and true positive rates, our goal is to only engage the customer on true positives, things that are actionable and relevant to the customer. Now, the reality is, because we're looking at a lot of network related events also, there's a huge amount of what I would call a false positive, right? So like the previous gentleman shared with us about looking at those anomalies. So 24/7, someone's looking at that, they see a little spike, they're going to look at that and dig in very hard to make sure that the network is performing well, that traffic can reach us, be processed and subsequently handed off well. And from a security perspective, let's investigate that spike or change in traffic to see if there's any malicious traffic inserted or mixed in with that. To do that, you have to have a proper mix of automation, because not everything needs to be done by a human being. Certainly, I love automation, and certainly will always have that as a part of the solution. But there are times where you need that highly available human being to go in and look at that particular situation, communicate it back. Now, where it becomes super important is the involvement with the networking team. And a lot of people think of the SOC and they think, oh, it's just security. But you have to have a lot of different skill sets in there if you're going to have a well-rounded service experience. So we'll go over to one of our network engineers who are typically CCNP, CCIE level people, just so you have a feel for the skill level, because it's not only routing, switching in an infrastructure. They're worried about routing, switching on a global scale involving the internet, not only from a DNS perspective, but also from a BGP perspective. And it's not unusual during a very large attack that maybe 60% of the resources are security leaning. The other 40% are network leaning, because we are looking for possible exhaustion points on the internet that need to be routed around. So we will avoid and manipulate the internet, basically, on how we want to absorb that traffic. And that's a fair amount of magic that goes on. There's a lot of resiliency from BGP and other tools that can be used that will automate a lot of that activity. But sometimes you have to work around different problem areas. One simple example is during COVID in the New York area, there were two major ISPs that had a peering link between them. And with that peering link, because more people were working from home, it was always saturated. So to make sure that our end user customers had the right experience, right, even though it's not technically our problem, we will manipulate the way we take in our traffic through traffic shaping to end up giving the customer the best experience possible. Next slide, please. So this is where, the ThousandEyes tool has been a tremendous help for us. One of the things that we struggled with a couple years ago was when the customer would say, hey, you're in front of us, this is your issue to figure out. And they're not wrong with that perception, but we want to partner with them in trying to solve those types of issues. The ThousandEyes product has been a huge help in us being able to identify where a problem may be and route around it. In particular, we use heavily the Internet Insights module that ThousandEyes has. And that tool has saved us a massive amount of labor and really helped us with our communications with our customers, because a lot of our customers obviously have this product also, and we can compare information from that third-party source. So it's been very valuable in helping us answer that question when it's tempting to say, hey, it's not us, right? We can prove it much better with that tool, in addition to the obvious monitoring endpoint services that are built into it. Next slide, please. So when we talk about scale and attacks, I wanted to just throw some numbers out. And these numbers are absolutely massive and really hard to consume. But at a high level, in just one day, the platform handled over 12 million SQL injection attacks. If we look at bot attacks, the bot attacks, there were over 14 million bot attacks in one day. The platform handles that. There's a lot of automation in there to make sure things go well with that type of activity. But to do that, you have to have massive scale. And when we talk about the threats, that some of which are listed here on the screen from a WAF perspective, the one that really concerns me and is a massive amount of labor to address is credential stuffing. So in one day, there were 151 million. This is not a peak. This is just one day. We just pulled some numbers. 151 million credential stuffing attacks made. So that's a real incentive to rotate your passwords or passphrase, whichever you prefer to use, on a regular basis, because I guarantee you that a large number of you probably have your passwords unfortunately exposed out there somewhere, and someone is taking them, knowing that we all saw what's in the news recently about Twitter, and hoping that you're using the same password in Twitter that you're using on your bank account, possibly. So, keep them diverse and spread out. But when we talk about scale, the platform has nearly 300,000 endpoints around the world, over 150 different countries that we're in and taking in information, because we want to be as close to the attack as possible, and we want to be as close to your end customer as possible to be able to serve their content properly or protect them as best possible. So on an average day, it's not unusual to see over 100 terabits of good traffic, and that's good traffic that's HTTP, HTTPS, so surfing-oriented traffic. The number goes way higher than the 100 terabit number I just shared with you. If there's a big sporting event that's being served, or there's a big software download that's going on at the time. So you have to have that combination of massive platform capacity mixed with the right level of automation and mixed with the right level of immediately available human assistance when there are questions or when there are attacks that need to be mitigated. Because at the end of the day, if we talk about DDoS, which is a simpler form of cyber attack as compared to a WAF attack, or certainly as compared to a credential stuffing attack, anybody can stop it. That's pretty easy. But stopping it while simultaneously allowing clean traffic to go through, that's where the magic happens along the way. Next slide, please. So when we talk about the types of attacks over time, and if we're focusing on WAF, it's very different. And I put two chunks of information up here. And I'm noting that globally, remote file inclusion is the #1 type of WAF or website type of attack out there. And in EMEA, it's SQL injection. So what we found out is that most attackers are actually close to the victim. They're in the same country, they have a relationship with them, it's usually tighter. Now there's an exception for that when it's nation state driven, which is a tough actor to fight, obviously, if it's a government, or it's direct criminal activity, right? Not someone trying to just do a simple scam with that. But it shows that attacks are very different in how they are leveraged according to where you are in the world. Why is that? Because there are different attitudes on how to protect your infrastructure that's different around the world also. So for example, when we see a threat come out and patching is required, for example, in a customer's infrastructure, our customers that are in the Japan region are very fast, very efficient at knocking those items down. And we can see the threats that are associated with those risks drop off very quickly. Next slide, please. So if we talk, moving forward, just talking about DDoS and not about the WAF types of attacks, this graph, if you look to the right, we see the upswing. That's an upswing in attacks that were over 100 gig in size, right? So this year has been exceptionally busy and different from a large attack perspective. Now, the overall number of attacks, that's always been increasing, but it hasn't been increasing at the same rate as IoT, Internet of Things, that are available out there to be compromised until recently. So it looks very much like a lot of threat actors out there are leveraging or realizing now that, hey, I can make money by selling access to my tool that will launch a DDoS. In the past, the DDoS was directly aimed at the entity they were attacking to try to say, hey, let's go ahead and get money, Bitcoin from them. I'm going to attack you again if you don't give me Bitcoin, right? We haven't seen as much of that with DDoS. It seems to have really swung over to political, social statement, those types of activities where entity A wants to cause harm to entity B. But next slide, please. So this is a snippet of DDoS across this year. Now, if we look at that far upper right attack, that was 1.44 terabits in size. Absolutely massive from a bits per second attack. Not the world's largest. The world's largest that I'm aware of that's been publicized was 2.3 terabits, shared with AWS. And I'll get into a little more detail on that shortly. But when you look at the lower right side, that gray, that in my mind, even though it's not high on the scale, that's actually the largest, most malicious DDoS, because that was 809 million packets per second, an attack that we handled. And the rest of it that's a mix of the different verticals and attacks that you can see. Now, I don't want to gloss over this because that bottom line, there are obviously this year hundreds and hundreds and hundreds of DDoS that were handled. But if you look at that scale, you can see that the vast majority of those were well above the 10 gig range. And I don't know how many enterprises out there have an available 10 gig pipe, right? So as soon as that gets any bigger than whatever that pipe to the internet is that you have, then that's a problem. And from a packet per second, you don't even need to have a large attack from a bandwidth perspective. And that's designed to knock your gear over. Next slide, please. These are the attacks I wanted to highlight. The AWS one, 2.3 terabits, was 293 million packets per second. Both are huge numbers, but the packet per second pales a little bit. Now, that particular attack was a CLDAP reflection in mass. So that is taking advantage of the amplification you can get by querying a server and having that server reply with a lot more bandwidth than the original request. So you can redirect those attacks at a victim. With the Akamai 1.44 terabits, it had an even larger packet per second attack mixed in with that. But that had 9 different vectors. So that attacker was super vigilant and really wanted to cause some damage out there. And that's actually a reasonably hard attack to handle because you have to understand what are all the vectors that are being aimed at the customer and what are the customer's expectation of that type of traffic and how do I clean that up. Then the other one was the 809. That was UDP in mass. That was UDP being aimed at 80. And then there's Cloudflare had a 250 gig, but very large, 754 million packet per second attack. And that was 2 vectors. So some absolute prize-winning attacks have happened this year on the DDoS front. Next slide, please. So I wanted to very quickly, just to stay on track and share some threat research snippets that I got recently from InfoSec. And the command and controls that are out there to launch those attacks, they're not really contested. They've done a good job of building them so that when you say, hey, I feel like renting 5 minutes of time at this much attack size, what do I need to do? They queue that up and they'll manage it. The problem is that there's infighting for the bots that are out there, what the items are that command and control is leveraging. So it's not unusual to have an attacker gain control, let's say, of an enterprise DVR out there, and another attacker gains control of it. They will actually remove the code of the original attacker so that they can maintain 100% control of that device. Because that device, it's not unusual, for example, an enterprise level DVR, to be able to put out 500, half a gig of traffic. That's becoming a problem for some ISPs where people always think about, oh, I'm the victim, I'm being hit by DDoS. For some ISPs, it's a problem for sending the data, right? So if you all of a sudden have your pipe being filled on the outbound for a customer, that's a problem to be able to clean up. The thing, again, to speed things up, to stay on track here, that the IoT devices out there, if they've been out there for a while and you think, hey, I want to secure them now, it's probably too late. They're probably already compromised. So the best thing to do, unfortunately, is reset them back to factory, patch them up, update the security around that, whether that is better passwording and firewalling, and then put it back onto the internet. Let's go ahead and move to the next slide, please. So what can you do? Number one is know your traffic. The number of times that I've been on the phone with the customer, I say, hey, how much of this traffic do you expect? It's not unusual for a customer to have no idea. They don't know their profiling. So take the time to understand your traffic, because if you don't understand your traffic, you're not going to know how to defend yourself. Build your defensive posture in advance during peacetime. There's nothing worse than being in the war. You're under attack, and you have to spend a gob of time figuring out what is the right level of mitigation that I need at that particular time. Come up with a plan B defensive posture. If there's a really horrific attack hitting you, understand what are my core services, HTTP, DNS, and I don't care about VPN and everything else in my network, and I don't care about traffic out of this country, but I do care about it out of that country. How can you set up a defensive posture that's the just get me back online? So have a plan A and have a plan B. Tie in your business continuity plan and your ERP, your emergency response plan, to your testing. I know it's horribly boring, but do your cyber hygiene, which is the patching, the proper passwords, the proper firewalling, and knowing your environment. Implement the right balance of automation and human. There's an architecture called Zero Trust that I'm a huge believer in. It's hard to transition to Zero Trust if you have a legacy network, but if you're building a new network, we don't have today enough time to get into it, but seriously consider a zero trust environment when you come up with that new architecture. Work with your upstream providers, many of which have been talking today about building that environment. And seriously, you have to test, and retest when you build something, because if you haven't tested your business continuity plan or you haven't tested your defensive posture, it's going to fail in a bad way. So you have to do that on a regular basis. Next slide, please. All right. So hopefully I left a little time for Q&A. I'm sorry. I apologize. I can't hear you.
Same issue of not muting myself or unmuting myself. Sorry about that. Thank you so much, Roger. That was a great session. A lot of really, really good data in there, kind of showing how not just, the network, the internet's doing with COVID, but what the impact has been from, a threat level perspective. So we did have a couple of questions come in. So thanks for leaving that extra time. So the first one is around, given the reported traffic increases in the wake of the lockdowns, COVID, were there any instance where normal traffic was confused with a DDoS attack?
No, there wasn't, because from the origin or from the customer perspective, we know the type of traffic and we don't generally trigger off of volume, right? So that can be very ugly if you set thresholds that say, hey, anything over a gig, start chopping off that traffic. That's going to unintentionally eat good traffic. So while we did see variations, it did not have a subsequent impact on DDoS or the mitigation. Where we did see problems is where we had to manage the internet itself away from the customer and away from our environment to route around problem areas.
Interesting. All right. The second question is, specific to, certain type of services that might have been targeted more than others, especially around, right now, VPNs basically are super critical for, productivity, experience, and all of that, because all of us are working from home. Was there any specific service that was targeted more in this time frame than previous pre-COVID?
Yeah. So where we saw the greatest level of increase was actually a little different. It was more infrastructure oriented, and it was on malware and direct phishing attempts to get people to click on something in their email openings, knowing that people are home, and home is frequently, unless you have a zero trust environment, a weaker security environment than in the office. That's been the big spike. There's been a spike in credential stuffing. If you would ask me this question towards the beginning of this year to pontificate on where we were going with it, I would have said SIP is going to be attacked and VPN is going to be attacked.
Right.
A little, very slight increase in activity on that front, but not anywhere near what I would have incorrectly assumed would have been a vulnerability in this new world.
Right. Okay. With respect to those phishing attacks, just me asking a follow-on is, how much of the type of message or the type of attack could you recognize? Was it, trying to accelerate and kind of piggyback on the criticality of COVID, or was it, similar to pre-COVID?
It was more targeted. So it would say because of COVID, and it would look like an email from your employer or from your bank, right? And it would say, because of COVID, please click here and assure your credentials. That's a simple example, obviously.
Right, sure, fair.
But yeah, the verbiage of the attack was absolutely changed. The methodology or the final exploit was not changed.
Got it. Okay, that's useful to know. Kind of, I would expect them to do that, right? Take advantage of the situation.
Right.
Yep. Well, Roger, thank you so much for the session. This was really great. If there are any more questions that come in, we'll kind of use them at the end of the show.
Awesome. Thank you, everyone.
Right. All right. With that, let me introduce our final speaker, Jeff Houston. Jeff Houston is the chief scientist at the APNIC Asia Pacific Network Information Center, where he undertakes research on topics associated with internet infrastructure, IP technologies, and address distribution policies. So with that, and the session is going to be really interesting. I know Angelique spoke about it a little bit in the beginning, so stay tuned for this. Jeff, welcome to the show. Just you're
Thank
still
you.
waking up? Thank you so much. I know it's really early for you there.
It is dark outside. That's true. Look, thank you very much for that. And it's really a pleasure to be here. The state of the internet is such an astonishingly big topic. You know, there's so much that we could talk about. How are we going with IPv6? Is the DNS still managing to do its job, or is it sinking under the strain? What about routing? Does routing even work anymore? And all this pressure with content distribution networks. What's actually happened to the shape of the network? What's the state of transit? Does anyone care anymore? Or has the entire internet been privatized by the CDNs? Who's building infrastructure? Who's left building infrastructure? So many things. But you know, what I've heard so far has actually been operations. And it strikes me that operations is largely reactive. It's sort of, this event is happening, I need to form a response. But the underlying this system is, why is it happening? How can it happen? Why is the internet so insecure that attacks are easy and defense is hard? How do we manage to make this so asymmetric? And if you go one step further in that how and why, you start to wonder about, what's the state of the technology itself? Are all the preconceptions, rules of thumb, all the decisions that even vendors make before it gets into operations necessarily reflective of what we really know, or is it just some mythology from 30 years ago? So I'd like to drill down on that very fundamental question: what do we know? And more importantly, what's changing and why? Because the internet is not chiseled in granite. We didn't have our best ideas in 1980 and then, you know, stop everything. We still have really good ideas, and things are changing. Things are changing quite radically. It's just sometimes it's not visible. Yes, it's pretty obvious that CDNs and CDN providers are massive, but I'd like to look at one particular area which is quite esoteric, but fundamentally really important, the heart of the internet. I'd actually like to look at protocols. Next slide, please. So I want to talk a little bit about evolution. And this sort of verb, I think, entered civilization and our discourse way back, 160 odd years ago. Charles Darwin published what was at the time a surprising book. Originally did a paper authored with Alfred Wallace, where they discovered the same thing independently around the process of, we call it survival of the fittest, but it's the process of evolution of biological life. It's the way life forms adapt to their environment. And what, of course, happens is this is natural selection, as he termed it. That what happens is things evolve because small changes advantage the entity that's changed relative to the rest of the species. And that relative advantage becomes prevalent. Next slide, please. So let's look at the pressures that are sitting inside the internet itself. In the 1980s, the internet we built was a kilobit network, clearly. We managed to make that into a megabit network, starting with the NSFnet and moving on in the 1990s. And the 2000s, we moved to a gigabit network. And then in the 2010s, we kind of stopped. Next slide. What happened? I'm like, it hasn't got much faster in the last 10 years. We haven't gone from gigabits to terabits. We really, really haven't. TCP itself isn't much faster. Next slide. You see, the optical guys didn't see that same sort of ceiling. What's going on in optical is we're now doing terabit capacity optical systems. We're heading way, way up in terms of what we can put across a cable, but the silicon isn't keeping up. Our switching speeds are actually not managing to keep pace with the underlying photons. Why not? Next slide. I'm going to do the next slide a lot. There are a lot of slides here. If we really want to understand why TCP isn't keeping up, we actually need to understand TCP itself. And if there's one protocol, just one, that I reckon is the internet, because all the rest is wrapping. You know, you could have wrapped it around DECnet, Apple Talk. not sure about SNA. And in fact, I'm not even sure about Apple Talk. You could have wrapped it around anything. But the beating heart of what makes the internet so phenomenally unique, so different, is indeed this TCP protocol. Because TCP protocol was one of those things that has self-adaptation, and it attempts to operate fairly and efficiently. Next slide. Now, fair and efficient are actually really, really big terms. Efficient actually means don't ever leave the ISP with bandwidth. Nothing is left on the table. If you're efficient, you go as fast as the network will let you, as fast as the clock will let you. So operators who go, yes, we operate 75%, we leave 25% for headroom. Not true. Not if TCP is doing its job, because there should be no headroom left. If you're efficient, use everything. Now, the other part of this is fair. Unfortunately, the internet wasn't built for me. Well, maybe it was. No, it wasn't, unfortunately. I have to share the road. I have to share the internet. And I have to share it fairly. I shouldn't crowd out everyone else. If there are 1,000 other people on the wire that I'm on, I should get around 1,000th of the share of that wire. That's fair. So when I'm trying to be efficient, I shouldn't kill everyone else in the process. I should even my pressure out. Next slide. So those are the design objectives. This is a flow control system. It's sort of fluid dynamics in a digital sense. Every single digital flow has to gently push all the other flows out of the way to signal that it needs a fair share, but not too far that it pushes them off the wire completely. That's the ideal situation. Next slide, please. So the way TCP actually works is it doesn't understand what the network's doing, and it doesn't assume that anything the network tells it is necessarily true. All those sort of feedback signals from the network might just be false. It might be someone else mimicking it. I have no idea. So I want to rely on signals I can trust. And the best signal I can trust is actually the echo of me. And the way TCP does the echo of me is that every time you send a data packet across the network, back comes an acknowledgement packet. And the pace of the acknowledgement packets, those ACK packets, is actually the same as the pace of the data packets as they're delivered at the receiver. So as long as I send a packet for every ACK, then I'm keeping pace, a constant pace, because in essence, every time a packet leaves the network, I can inject a packet into the network. Next slide. Now, the issue is, what point is that steady state achieved? What's fast enough? And so we don't know. TCP doesn't know. There's no rationing going on. This is not a circuit-controlled system. We're not running 64K anymore. I need to probe into available capacity to figure out when I'm too fast. And a little under too fast is fast enough. And so the way we originally thought about this in the 1980s, and it is a long time ago, was that when you drop a packet, that's too fast. Next slide. So this is the classic TCP protocol called TCP Reno. While there's no packet drop, gently lift up the pressure on the network. One new packet inside this conveyor belt every round trip time interval. If there's no packet, if there is packet loss, react like crazy. The car has crashed. Decrease the sending rate dramatically. Drop it by 50% to halve the sender's window. Next slide. So what we get out of this is the classic TCP sawtooth picture. That rate halving is actually incredibly important, because what goes on is that as you're increasing the pressure on the network, queues are forming. And as queues form, the queue gets bigger and bigger and bigger and bigger. Till eventually, of course, the queue fills and a packet drop occurs. When you rate halve, you actually go silent for one round trip time. And what you want is the queue to drain completely in that round trip time, so that when you start again at half the rate, the queue is empty and you can do it all over again. So this is the classic sawtooth response of TCP. Next slide. So the theory is that if you're memory sized inside the network, what the operator's doing in the network matches what the sender protocol is doing over in the host, you can actually make this queue behavior precisely aligned. So how big should the memory inside the network be? How big should those buffers be? Well, interestingly, it should be the size of the delay bandwidth product. So if you're driving a gigabit link over a 1 second delay, you actually need a gigabit of memory, really fast memory in your line card to make all this work. The queue size is the delay bandwidth product of the link it drives. That's the rule of thumb that vendors have been building to for the last, 30 odd years. Next slide. Now, all this works with the single assumption that it's just me. And as we'll see, that's probably a bad assumption. It's not a one flow network. It's a million, billion flow network. And all of a sudden things are different. Next slide. So this is what I've said. The size inside your network, what you provision, is bandwidth times round trip time. And that was a result published in 1994. Don't forget, by the way, this is the most expensive memory almost on the planet, because what you need inside these line cards is not slow memory, not memory coming off, the normal production lines. You need memory that is as fast as you can possibly make it. Because if you're trying to go at a gigabit speed, you actually need memory that can give you gigahertz bandwidth. And that is not easy. Next slide. So if you make it too big, what happens? If you overachieve and stuff in way too much memory, oddly enough, all Reno will do is do the same thing, but leave queue bandwidth on the table. It won't drain completely. So that if your queue is too large, you're just inducing delay, which of course is not exactly user-friendly. Next slide. And what if it's too small? Well, maybe too small is an even worse sin, because when it's too small, you actually overachieve. And when you rate halve, you go below link capacity. And so it takes some time to ramp up again. You're leaving bandwidth on the table, and that's inefficient. Next slide. So what we'd like to do is change things. And at this point, Darwinism takes over, because I can't change the bits in the TCP header. That's invariant. But what I can change is my behavior as a sender. And the real question is, can I alter that algorithm to actually be no less aggressive than everyone else? I want my fair share, but maybe eke out corners of bandwidth and capacity that other folk aren't doing. Maybe I should be a little bit more responsive, react faster. What I can't do is destroy the environment. I can't eat up all the bandwidth because everyone else dies and then they're going to come back and kill me. So in some ways, this is almost like a survival Darwinism issue. I need to be just a little bit better than everyone else if I'm going to take advantage of the situation and thrive. So this is what's been happening for some time. Very few folk use Reno now. Next slide. We've done all kinds of theories. There's been a zillion PhDs on the topic, and some of the ideas are quite unique. One of them, which I kind of liked, was, well, if I get 1/1000th of the share of the bandwidth by using Reno, why don't I multiply all my factors by 2? Instead of rate halve, I rate quarter. Instead of increasing by 1 segment every RTT, I increase by 2. I behave as if I'm 2 sessions. Well, 3, 10, 1,000. Why don't I oscillate at a very high frequency? Mul-TCP is the way that algorithm works. And in limited applications, it's actually not bad. But overall, you tend to consume the network, destroy the environment, and everyone's unhappy with you. So are there other methods? That linear increase, for example. Next slide. What if we explore mathematics and use a polynomial equation like, a cubic? And interestingly, what you do in a cubic equation is move very quickly to what you think is the sweet spot and then oscillate more slowly around that spot of packet loss. And if there is, if you will, available headroom, again, you move very quickly to occupy it. Next slide. Now, the sawtooth pattern of Reno is changed in cubic to almost a polynomial shaped pattern. But what you actually find is that it tends to oscillate around packet drop. And what that means is the queues are always full. The bigger the queue, the longer the delay. So in this case, what's going on is that the queuing factor inside the routers is actually decreasing performance, not increasing it. That's bad. Next slide. So Cubic can react extremely quickly, faster than Reno. It's adapted in that sense. But in some ways, it's slow in terms of it's putting packets inside buffers and it takes time to drain them. So it exacerbates buffer bloat. That's bad. Next slide. The real problem is in all of this, it's not one flow. And all of the work so far in terms of flow control has actually been about a single flow. And the idea is, well, if it works for one, it'll work for a billion. Not true. Next slide. Because in some ways, it's about how these flows self-synchronize. If they're precisely in phase, then yeah, it's all going to require the same buffer space. But what if they're out of phase? Well, oddly enough, it's going to only require half the requirement of buffer space. Next slide. So in some ways, we can do a lot better than this if we think about the problem we're solving without changing anything and just looking at the interaction of multiple flows. Oddly enough, you don't need anywhere near the memory you thought you needed in your router. You need that bandwidth delay product divided by the square root of the number of flows. If you're taking 100,000 flows across a switch, you only need 1/100th of that delay bandwidth product. This was actually quite an old result, 16 years old, but vendors are still selling you enormous amounts of memory that actually is just really adding to delay, not adding to performance. Next slide. So why do we actually have buffers? Why do we actually put packets in a holding room before sending them out on the wire? And there are two reasons. One is, of course, multiplexing n flows into one. If they all arrive at the same time, everyone else has to wait for the first one to go out, n into one. But there's another reason as well, and that is most hosts are incredibly ill-mannered, impolite. They burst, and that's the wrong thing. When you burst, some buffer in the network needs to splay that burst out and even it out and make you a more polite sender. What if you were more polite? Next slide. What if you rate paced? Well, if you rate paced and distributed the data over the entire round trip time interval, oddly enough, you make much less pressure on network buffers. And oddly enough, you can go faster. So sender pacing is a really good idea. Next slide. If we all paced, if we all were polite to each other and actually paced that information out, we'd actually find we hardly need any buffering at all because we wouldn't form standing queues. And the amount of buffer space we need is actually much the same as the log of the average flow window size. And as long as that is effectively spaced out, it's a really tiny number. Why is this important? Next slide. Because if we can change the demands on memory, we are winning. Oddly enough, silicon hasn't all gone at the same speed. Processors have gone a huge amount faster, but they've gone faster over the last 40 odd years because of parallelism, not because of fundamental increases in the clock speed. Memory is really just a clock speed problem. And oddly enough, over that same period, memory speeds have gone up by a factor of 10, really slowly. So when we've got these ultra fast networks, we haven't got memory to keep up with it. Next slide. Why is that important? Because the chip. Because when we're designing a switching chip, we have to design the switch and we have to figure out how to do the memory for that switch. If it's on chip memory, then it can be quite fast, but the chip size hasn't changed an awful lot. So on the chip, 16 meg to 64 meg, no more. Now, if you do, I'm going to go external memory, that's great. You can get gigs of memory. But now you've got an external memory interface, you've got a bus, you've got all kinds of tricks to make it go. But that also takes up chip space. And oddly enough, on a switching chip, you actually spend up to 60% of that real estate to do memory control. If you can reduce the memory and actually say, I'm only going to use a fraction of the memory of the delay bandwidth product, you can make switch chips which are awfully fast. Next slide. And by awfully fast, I mean, wow, 1.8 terabits of switching capacity. This is how you make silicon work as fast as optical. You make it work by having only 16 megs of memory on board on the chip. Interestingly, it even has in-band telemetry, but the key thing is it has no memory, almost none. How do you have a protocol that can use that? Next slide. So now the pressure in terms of Darwinistic pressure is to actually understand flow states as they relate to queues and memory buffers. Next slide. Because what you're trying to do is actually optimize at the point when the queue forms, that point at the left where the round trip time starts to increase because the queue is forming. Because at the receiver, once queues start to form, you're getting no more data delivered to the receiver. You're working at capacity. Now, all these loss-based congestion control points work at the other end, over at the right, when the disaster has happened, and not only have you filled your queue, but the signaling system has failed. Next slide. So how do you detect the onset of queuing? Well, one way is to get the network to tell you. Next slide. This is something that was developed in the 2000s. Sally Floyd's group did this. And the idea was developing on an idea from digital back in the late 90s, I think, maybe early 90s. Explicit congestion notification. When queues are forming, mark a packet. So the network marks the packet on the way over to the receiver. That mark is put back in the axe. The axe is sent back to the sender. I know when queues are forming. I can now go as fast as I can until I get that notification. Next slide. Now, there are many things about this that are good. It's a single bit. That's great. But everyone needs to be aware. Everyone needs to mark these bits and receive the bits. Apple experimented with putting those bits in. Hasn't been a success. Why not? Next slide. Because it's a bit like security systems. Security only marks what's good. And if everyone does it, then if it's not marked, it's bad. But if only half of you mark what's good and it's not marked, I actually don't know if it's bad or not. I have no information. So unless everyone does it, it doesn't really work. And that's the same with ECN. Partial adoption is a signal that says, meh, well, nice try, but useless, which is a lot about security too, but that's a different talk. Next slide. So we can't make the network do the marking for us. We have to do it ourselves. We need to detect the onset of delaying. Next slide. I told you the slides were fast. We could use a system that actually detects the onset of queuing, not by making massive adjustments in response to packet loss, but by making small adjustments continuously that detect the onset of queuing. So you're constantly pushing in going, did a queue form? Did a queue form? Did a queue form? Next slide. And this is the principle behind a protocol recently, well, not recently, it's about 6 years old now, developed inside Google called BBR, bandwidth delay. So what it does is it paces the sending packets, pacing is good, and it probes every 8th round trip type interval. And the way the probe works is increases the sending capacity by 25%, which is a pretty big increase for one round trip time. And then it decreases it by the same amount for the next round trip time to drain the queue. And it looks very carefully at the delay, the round trip time delay on that probe when it increased by 25%. If the delay didn't change, yahoo, we're in business. Increase the sending rate. Keep up at that 25% increase and do it again in 8 RTTs later. If we found a little bit of delay, whoops, we've actually managed to trigger queuing. Don't make any changes. Don't alter the path bandwidth estimate because of packet loss. Why not? Because packet loss is erratic. Ignore loss, just look at delay. Next slide. And so now, instead of having a sawtooth, we have an entirely different profile that we actually establish the fair and efficient sending rate, network capacity, by basically probing into the network queue in short, sharp bursts, which actually take very little buffer space. You can actually build gigabit networks with megabit buffers, and that's a fantastic result. Next slide. The problem is, of course, fairness. And when mammals and reptiles meet, one or the other has a problem. And when loss-based systems and delay-based systems compete, one or the other is going to have a problem. Fairness is an interesting question with BBR, because what it does is it doesn't back off with packet loss. It keeps the pressure up. And so when you put a single cubic session to compete in red with a single BBR session that comes along 20 seconds later in green over a 10 gig wire, about a 30 millisecond round trip delay, BBR just wins. BBR is much, much better attuned to actually running at network capacity with making minimal demands on memory. Cubic, the reptile, doesn't. It relies on massive memory buffers to work efficiently. When BBR comes along, it kind of dies. Next slide. So in some ways, what we're seeing is a classic environment for evolution, a classic environment of survival of the fittest. Because what we're seeing at the moment is in the zoo out there, there's an awful lot of TCP control protocols. And whether it's Cubic, New Reno, Leadback, I think Windows use Leadback, Fast, Akamai use Fast, or BBR, Google use BBR a lot. All of these TCP control protocols are actually pushing against each other and jostling. BBR is actually trying to do it quite differently from most of the others. It's not actually using loss as a signal. It's using this probe delay as a signal. In some ways, this rich environment of competing protocols actually forces us to consider what's fittest. There's also a whole bunch of traffic models, because in some ways, all those video streamers, all of these Windows Zoom sessions, all of this DNS, there's a huge amount of different bits of traffic. And of course, that's just part of the environment. And all those queue disciplines that you network operators use, all of you have picked your favorite one. The poor packet and the poor flow running across all of them is getting a huge mixed signal, because you can use red, weighted red, Codel, fair queuing, and all these kind of queuing disciplines. But of course, consider the end-to-end system. It treats all of those as damage, and tries to optimize its behavior in spite of what you're doing. And of course, it's not just a single wire. There are all kinds of wires and wirelesses. There's cellular, there's Wi-Fi. They all have loss characteristics, delay characteristics. And of course, none of you have figured out how much memory to put in your routers. Your vendors would like you to put in bucket loads because it's so expensive and their margins are great. But oddly enough, the chip designers are scratching their head going, oh my God, this is a real problem. Can't put that much memory on the chip. And of course, there is some ECN out there for what it's worth. Next slide. So what wins? Inside all of this, it's not just what I'm doing is fine, I'll keep on doing it. Because oddly enough, we are changing everything all the time. And if efficiency and fairness need to be put on scales, and it's either you can have one or you can have the other, I actually would favor efficiency, because an efficient protocol that makes astonishing use of the network and leaves nothing on the table is going to naturally win in this place, and everyone else will be using it too. So protocols that make minimal assumptions about the insanity of what vendors do inside the network, the insanity of what even operators do to try and control the network. If the protocol can work in spite of that, that's a protocol that's fittest. And my suspicion is that protocols that constantly use feedback, that regularly, every 8 RTTs or even more, probe into the network and try and sense the network, are going to be far more robust and actually alter the internet fundamentally and put up an entirely new model of the way we use communication systems than the protocols that rely on irregular car crashes. Packet loss is a disaster, and driving our networks from underutilized to disaster to underutilized to disaster is a hopeless way of running a network. It's a hopeless way of running a road system. It's a hopeless way of running any of these systems. We need to change to make the internet run faster, run more efficiently. And the issue is right now, it's not the network anymore. Putting tricks, putting facilities, putting services inside the network infrastructure only makes life worse. If we actually did less in the network, less memory, less packet mangling, less state, less overhead, and pushed the entire problem back into end systems, we'd actually have a better network. And interestingly enough, that's where we're going. This is not just operating systems anymore. Most applications have given up on their platforms. Quick is a classic. Quick, the internet sort of system used inside Google's Chrome browser, has lifted the transport session up into the application. All the operating system sees is a bunch of UDP packets. They happen to have an encrypted payload, so all the network sees is nothing. Applications are now doing their own thing. Applications understand their own flow. There's enough space inside everything, including this little device here, to actually do an astonishingly sophisticated effort at managing the flow as an application. So what we're actually seeing inside this protocol Darwinism is not just a change in TCP. That's a minor thing. What we're seeing is a far more major change where the network is being relegated, where the operating system platform is being relegated, where the application itself is asserting a degree of ascendancy that is now, if you will, the major player in this network that we're seeing. This is now an application level network where the network protocols themselves are up in user space and actually making far better use of the network than anything we've ever done before in the platform. So in some ways, this protocol Darwinism is incredibly fundamental to the argument of what is the internet today. And if you think it was a bunch of networks interacting with a bunch of operating systems, with a bunch of dumb applications streaming across it, that was true in the 1980s. It's not true today. It's almost the opposite, that the application itself is now the master inside all of this. I think that's the last slide. Next slide, let's see. So what do we learn from this? First thing, rules of thumb are rubbish. Rules of thumb say, God, I don't know why. I'm just going to do it because everyone else has done it. That's crazy. We don't know that much about how to make extremely high-speed systems work. And over-equipping your router with memory is a really dumb thing to do, but everyone does it because it's a rule of thumb. Why? A cherished assumption, but it's wrong. If we really want to make a terabit network and even a petabit network sing and dance and do phenomenal things, we need to think differently. We need to continuously challenge our assumptions. And the beauty of all this is that the state of the internet tomorrow is not the state today. That the internet still has an extraordinary set of really important problems. And if we just operate our network and react, we're not going to meet those problems and we're not going to make it better. We're just reacting. If we want to move ahead, we actually need to treat the network as a malleable thing and treat the ecosystem in the same way that biology treats its own ecosystem, as an environment where adaptation wins, where changes actually create disturbances that in turn create efficiencies and opportunities to exploit. And so the beauty of this is there's a lot to learn about the internet, and I think we can all have a lot of fun in learning it. Thank you very much. I'll hand it back.
Thanks, Jeff. That was great. It's always interesting to hear your perspective on things. And so we actually had a question come in from Twitter while you were speaking. So the question from Andrew Campling is, with regards to the current and future state of the internet, is it suffering from ever more focus on optimization of web apps at the expense of everything else?
Hi, Andrew. Is web apps rather than everything else? Well, in some ways, I suppose, we managed to create a security infrastructure out there, a set of ever narrowing apertures where the only thing that makes it through these paranoid devices is TCP port 443. And this is really sad. This is really sad. Because in some ways, if that's the only thing that gets through the aperture, that's where we all crowd.
Right.
Now, if we hadn't been so stupid in developing paranoid security systems that just did damage and actually tried to understand the problem we were really trying to solve, we wouldn't be in this mess. But these days, if I want a protocol that works, even the DNS and I don't use port 443, then I'm in a really sad place. And so what we actually find is there's a bit of UDP and a bit of TCP and everything else gets dropped. We found with the V6 transition, we wanted to use a new protocol number 41, IPv6 and IPv4, disaster. Why? Firewalls. We tried all kinds of tunneling mechanisms, disaster. Why? Firewalls. And so in some ways, everything is a web app because that's the only thing that gets let through. It's not because web apps are good. It's probably crud. It's probably really bad. But if that's the only way to make it through, pragmatism says that's what I'm going to use. Everything else gets layered above that. And so, yes, Andrew, sadly, even the DNS is now a web app.
Yeah, I guess I shouldn't ask for your opinion on DNS over HTTP.
You just got it.
Okay. That's great. We'll let you know if more questions come in. We have some of our speakers on as well. And so we're going to come and bring some folks on. We have, let's see, Archana, you have a question for our speakers?
For Marcel. Marcel, are you on? Hey. So the question that came for you is, are there situations where no matter the configuration you try, some users are impacted in favor of others? The follow on to that is, how do you determine the configuration to go with and what is it based on?
Yeah, so this definitely does happen, right? And you know, at the end of the day, it's kind of an unavoidable reality, right? Some users just, there's no configuration that creates good performance for them. And at the end of the day, this is ultimately perhaps a large scale architecture decision that maybe is a little outside of my purview. But it's ultimately not really any different than other sort of growth decisions, right? If you're trying to decide where to put a new point of presence, you're actually going to have to make the same types of decisions, right? About which users are most important to being served. You know, a lot of times it's focused on decisions like where can we have the biggest impact across the most users, right? Which networks can we help the most? Sometimes it's about there are certain networks that we otherwise have poor coverage for, so it makes sense to sort of baby them along a little bit. So it's very case by case dependent. I would say there's maybe not there's not sort of uniform policy that we can apply, but I would liken it very much to general sort of expansion planning.
Mm-hmm.
Thank you, Marcel. Angelique, the next question I think is for Jim and David.
Yeah, so the question for Jim was referring back to your comments on VPN and local peering. So what do you recommend for enterprises that are looking to fix these performance issues for workers that are working from home? How do they go about working with service providers, for example, to address some of these performance issues?
Sure. So I'd recommend that the enterprise, first of all, do a survey of their employees and find out what are they using at home? What are the providers that they have at home where they're doing their work? And then armed with that information, they can decide which provider or providers is the majority of their user base, and then talk with that provider. Unfortunately, a lot of providers have historically had the attitude, particularly if they're smaller telcos, that the way to fix this problem is you buy a connection from them for your enterprise and now your problem is fixed, but it's only fixed for you. It isn't fixed for everybody else. So that's generally the answer that most of the suppliers want, but obviously having discussions with them, particularly if you have some economic incentives to offer in terms of doing business with them, and try to convince them to do more peering publicly. But certainly, if you absolutely have to fix the problem for your enterprise, buy a connection from that other provider.
Good advice.
David, question for you. You've been tracking disruptions, internet outages for a long time now, right? And so what is it that you've noticed or something that's changed, stayed the same with, from the perspective of lockdowns?
Sure. Yeah, and it's an interesting question. It's something I've been actually thinking about for the last couple of months as well. I think that we've seen internet disruptions due to network issues, fiber cuts, cable cuts, things like that. Those have more or less continued apace. I think you're always going to have errant anchors and configuration issues and things like that. I think what we've seen a decline in over the last couple of months have been the large-scale government-directed shutdowns. The 2-week shutdown in Ethiopia that just kind of ended, notwithstanding. But I had been talking to some colleagues about that as well, and there was this question of is that decline because governments are finally realizing just how critical the internet is for everybody's lives now, thanks to the pandemic, thanks to the lockdowns. But I think what we ultimately realized is that it's less that, unfortunately, and more that a lot of the events that historically drove the shutdowns, the riots, the elections, the things like that, those have been not taking place, or they've been postponed, or the elections have been postponed, the riots haven't been taking place, depending where you are, of course. But those sorts of activities, I think, are happening with lower frequency right now, which is then driving the governments has been driving fewer government-directed large-scale internet shutdowns. And I'll use this as an opportunity also to plug my blog, internetdisruption.report, and work that we're doing at the Internet Society as well on the Measuring the Internet project, looking at internet shutdowns.
Thank you, David.
We have a follow-on question for Jeff, if he's still on.
I certainly am.
Andrew has a follow-up question to your response. So he has said, if everything morphs into web apps, how do you see this impacting open standards, security, and ultimately privacy? He's pessimistic, he said.
Oh, I think it's perfectly reasonable to be incredibly pessimistic about the internet. Indeed, trying to search for something that hasn't quite got this sort of ring of acute pessimism is at times quite challenging. The early days when we thought this opened up broad horizon of digital communication, where any protocol was possible, any form of interaction was possible, where we discovered and were playing with all kinds of methods of communication, sort of vaporized at some point because we abused that environment so horribly that everyone put up filters and firewalls. And this response to this level of abuse is actually almost worse than the problem it was trying to counter. That we are locking this down now and creating intermediaries, creating a brokered communication environment, all in the name of enhanced security. But of course, the fundamental observation is, if we're relying on security being prime number factorization, the first quantum computer that works will blow that out of the water. If we're relying on security being a bunch of CAs that never ever lie except when they lie, then again, this whole stuff is terrible. So I can share Andrew's pessimism that we're building a very encased internet and trying to think that the little bit of greenery we've managed to fence around is greenery worth living in. The problem is it's probably not. And the issue is, I think, in some ways, what we don't do is look further afield. We don't measure, we don't observe, we don't feedback. We are constantly just reacting and very little understanding. And I think part of it is that we kind of lost the research and academic community somewhere down the path of commercialization. And somewhere along this, we kind of assumed, well, this is all done, this is all fine, thank you, boffins, you can go home now. We understand this so well, we're just going to exploit it for what it's worth. But I think that feedback loop of understanding what's going wrong in exploitation is missing. And creating ever more draconian firewalls and shutting the apertures down ever more highly, and creating systems where the poor operators, as we saw at the moment, are pulling what's left of their hair out, trying to balance traffic. This shouldn't be happening. If we can make self-driving cars, why can't we make self-driving networks? What is wrong with us, and why we managed to get it so thoroughly wrong is actually a really, really good question. We don't understand what's happening. We don't watch closely, problem A. But B, we actually don't think about what we've just seen and put it into context and understand where to go from here. And so the result is, as Andrew observes, we lose privacy, we actually lose flexibility, we lose a whole bunch of things that in the long term are valuable. And so, yes, this is not the ideal place to be. I'm sorry, it's just not. And trying to understand how to make it better is, I think, the challenge for all of us. And I would encourage folk, the researchers are not dumb. The researchers are actually part and parcel of an ecosystem that hauls us back out of this mess. So thank you, Andrew. Good point.
Well, maybe that's not too pessimistic. So we have a open question to anyone on any one of our speakers who would like to comment, and this is, about the segmenting and closing off of the internet with actions by Russia or things like new IP under the Chinese government. If any of our speakers want to comment on that. So the question is about, how effectively the internet is kind of fragmenting, or becoming different internets, if you will, given Russia, given China, and there was some specific reference to new IP under the Chinese government, which I think you've written about, Jeff.
Yes, I did. Yeah.
Yeah.
I actually think new IP is a throwback to the 1990s. What is being, I suppose, proposed inside this model is back to a model of dumb applications, dumb hosts, and clever network. It's the whole QoS thing all over again. The internet is a scarce resource. Applications don't know how to make use of it. The network itself will arbitrate, manage, and massage traffic and actually control the applications. Now, if you're a vendor of network equipment, everything I've said is wonderful, because all of a sudden you're the center of the spending. You are the gatekeeper. You're the toll box. You're the reason why routers cost millions of dollars. The thing is, no one else believes you. And no matter which learned committee of greybeards you go to in the ITU, the answer is the internet is a marketplace. And what fuels the internet is my money and your money. It's how we behave. And if we want Chrome to do wonderful things, if we want our browsers to leap over tall buildings, if we want a different network, our money makes it. And so in some ways, I think the Chinese stuff is really just regressive, badly thought through, focused on all the wrong things. We've been there, done that, and moved on. And quite frankly, is doomed for failure in exactly the same way that OSI was doomed for failure. It's the wrong approach. We've lived that life. We're moving on.
Cool. Okay. So another question that's come in, this one, maybe, I don't know if you can answer this, Jana. So this is around how CDN use has changed for customers. Has there been anything in the wake of shutdown in terms of like maybe what they're caching on CDNs, how they're using it to better optimize traffic delivery? Have you seen anything like that?
So off the top of my mind, I don't know if anyone's changed their config significantly. I mean, I certainly haven't heard of any patterns of changes happening across the board, but one thing for certain is that customers who are seeing surges are relying more on our CDN and also on facilities like shielding. So we offer this 2-tier thing where you can put a shield node in front of your origin server so that across multiple POPs, requests get collapsed on their way coming to your origin server. And again, those are all just ways of scaling your service across the world. And that's, I think that broadly speaking, customers who've seen surges definitely rely more on our services. But I don't know that there's any pattern as such. So changes in configs.
Right. But maybe using more of the security features or using it to, as you said, shield their origins, maybe using like hierarchical approach to the CDN deployment. Is that what you're referring to?
Well, sure. Yeah, that too. That's certainly in part of the shielding that we offer. But I think, yeah, broadly speaking, again, it's reliance on facilities and on organizations that allow you to scale. Fastly is one of them, and that's the sort of thing that we see.
Cool. And did we have any questions come in, Archana, or did you?
No, I'm just looking at, no, I think we're done with all the questions. I don't see any new ones pop up just as yet.
Yeah, I think we've had some comments come in, which are interesting. So yeah, I mean, this was really interesting. The kinds of questions that have been posed, a lot of them have to do with, the sort of the kind of the fragmentation of the internet is one thing, in terms of where we're going, and then we had the questions about how everything seems to be kind of funneling into like this kind of very web app focus, even something like DNS. So kind of interesting to see where everybody's going in terms of what their concerns are.
Yeah, totally. I was just kind of, as taking a look at these questions, thinking back on some of the sessions and some of the highlights. One thing that Jeff mentioned on the ECN piece sounded really like RPKI in the BGP world. Like, until everybody does it, there's really no purpose of doing it. So I thought that was
well, it's like the same thing with DNSSEC, which it's
exactly.
like, unless it's adopted widely, then it's not, it doesn't work.
It doesn't serve its purpose. Yeah, totally. And then Roger's session talking about not underestimating planning and like planning ahead when there is no pandemic or there isn't anything coming crashing down or burning is something that I think we can take across, like use it as an advice across all segments, right? Not just about internet or building networks. So that was interesting.
Yeah, absolutely. So, I mean, despite the little disruption that we had initially, it seems like we are back on track. And it was really great to hear from everybody. Luckily, it was smooth sailing after that.
Yeah.
But if anybody has any questions that are follow-ons, feel free to drop us a note either on Twitter. We're at ThousandEyes, or you can drop a note to the show. That's internetreport@thousandeyes.com, and don't forget to subscribe.
Yep.
This was really great to have so many folks come from the content delivery side and from the research side and share what they've seen and how they've addressed performance issues and content delivery issues. So
right.
And
I'm hoping that, over time, kind of, to the point we were making earlier, Angelique, is like enterprises providers, like other than the NOGs, kind of creating that forum where you could exchange ideas and have these kind of vendor agnostic discussions. I mean, that's really the point of when hosting a show like this. So I think over time, I'm looking forward to that evolving and kind of creating this community where, we can come together. All right. With that, if you have, again, any more questions, feel free to send that in. We'll get in touch with the speakers and, get their perspective on it as well. And then if we can just throw up the last couple of slides in there before we, take off. Just a reminder that we are again on the podcast every week. You're going to see us again next Monday. We have some interesting outages and events to cover, an outage that happened earlier this week. So we're going to talk about, I think, was it WhatsApp? I believe it was WhatsApp.
It was WhatsApp, yeah.
It was WhatsApp, yeah. WhatsApp went down. We saw something that we could talk about. And again, if you have any interesting guests, or if you want to be a guest on the podcast as well, definitely reach out to us. Then Angelique onto the report. it's
Yeah,
released?
that's right. So just, we previewed some of our findings earlier, and we're going to be releasing in a couple of weeks. So stay tuned, and we'll provide more information on where you can download that report. So check it out.
All right. Thank you. And thanks for being a part of the show. We'll see you all in our podcast.
Thanks for joining, everyone.